Okay, we're getting ready to get started soon. We are going to get started. No? Yeah. But it's not going through the speaker system, is it? I don't think people can hear it in the back, is it? Or no, but like this is this way everybody else has been standing like this. Yeah. But yeah. Ty Connor. Oh. There we go. It's so strange. Yeah. So for the people online, we were just getting people seated here in person, and we are going to continue with next session. That's a mix of different topics. It's going to be a little bit, I'd say, PVT heavy, the first two presentations. So it's good that we got a little lunch in, because this can be a little bit heavy on the brain, as we usually say. And the first presentation is by my dear colleague Marcus Hayes Nilsson. He's the son of Curtis as well. And maybe I didn't have to say that even, but we are also good friends in addition to colleagues, and he will go through Whitson PVT, which is our essentially our fluid management system for everything that has to do with PVT. So with that, Marcus, I have your slides up here and also your clicker.
So do you guys prefer if I just stand here or look down, or take the microphone and okay, I'll try to stand here. I'll probably turn around, then you can't hear me, and then I'll turn back, and then but it's fine. It's PVT. Most of you guys probably are not that interested anyway. So I'm sure Matthias doesn't like me, and you know why? This is the third whitCon, and it's the third time I've been forced to present about PVT to a room full of RTA folks. Well, I'll do my best here. There are no equations or nothing too heavy duty, but you will have to learn some PVT. I'm sorry for that. All right, let's get started. How does PVT affect your work, and why should you care, right? That's really the reason that I'm here today. And so I want to start off by building a little bit of motivation for why I think PVT is important. And so we're going to take a look at just some day-to-day PVT situations here. And typically, when you think about PVT, you have your PVT reports, which is a combination of some Excel files, some PDF files, scattered on some OneDrive document that somebody has access to, and you have to ask very kindly if you can get them. And then you have your fluid models, the same situation. You have unless you have Whitson Plus, I guess, there you can have it in the platform. But you basically have a bunch of different files, something like that. And you need to know which one is the most recent, and you have to go and access that and make sure it's the right one for your situation. And then you have the calculational side of things. There's a lot of different things here. Calculation of the phase envelopes. You need to know your saturation pressure for your reservoir, looking at the liquid relative volumes, and just getting your BO, right? If you've got not a lot of geologists here, hopefully, but they usually ask for the BO. And basically, Whitson PVT is trying to encapsulate all of these things. Okay, so we want it to be a single platform for everything kind of PVT related. So let's take a look at some examples where we might need some help. The first thing is basically just, where's my PVT report? And not to mention that I've paid between $10,000 and $50,000, depending on how fancy the PVT experiments are, right, for that report. And sometimes there's 5 versions of it. Sometimes you don't know where it is. And I can promise you, everybody in here who works for an operator, you have lost at least $100,000 worth of PVT data just because nobody knows where the file is. Okay. Second example here. Let's say we're reservoir engineer, production engineer, or something like that, and we need to find our black oil table. Okay. So the thing that happens behind the scenes when you get a black oil table is that you start with an equation of state. Right? We're not living in the 1960s or 70s anymore, so we don't use the PVT data directly to get our black oil tables. So we have an equation of state. That equation of state has made a bunch of different black oil tables with a bunch of different surface processes and everything like that. And you can database all of those in Whitson PVT, which is nice, but you still need to figure out which one I should choose. And so this is where the expert comes in and says, based on my opinion, whatever, PhD in PVT or whatever that is, you can say this is the one that I should use, and you can mark it as primary, so that when you go in there, you don't have to think about which one you should have out of the 12 that are available. You just say that's the primary, and so you can go and say I'm just going to go find my BOT in Whitson PVT, and then zoof, you get that one like that. And the nice thing here is that Whitson PVT also keeps track of where it came from. Okay, you can see who made it, when it was made, and what process was used to make it. Okay, so it's not hidden. It's not just a text file. And I can't just be talking about, you know, PVT data and models because you guys are RTA folks. So I'm gonna show how little RTA I know by plotting GOR versus time and pressure versus time. And I apologize, I haven't done this since I was at university, so hopefully this is correct. Basically, let's say we have a situation that looks like this. We have our, you know, undersaturated production for a while, and the pressure goes down, if I remember correctly. And you can try to forecast what this pressure decline is going to look like. I just made it a very nice little curve there. So how does PVT impact something like this, right? Well, if I guess, or if I have a saturation pressure, which is on that blue line there, I'm going to get behavior on the GOR, which is going to look something like that. It's going to be flat until I reach the saturation pressure, and then the GOR goes up, right? So you get more gas coming out of solution, and you're producing that gas. If you have a bad estimate of the PSAT, it might be further down, and then the curve is going to look like this. And in reality, you can see the data points are going to be following that blue curve, roughly, right? And so knowing what your saturation pressure is can have an impact on your RTA workflow as well. Okay, so it's not just finding the lab report or finding the model. You know, you can ask us at Whitson about that, but it can have an impact on your production as well. So this is the part where you're going to have to learn a little bit about PVT, okay? Whitson PVT is trying to be a platform that follows your fluid from sampling all the way to the modeling. And if we start by taking our sample down here, that sample is then going to be transported to the laboratory where it's going to be stored for some period of time, right? And you're paying money for having this sample being stored. And a lot of companies are paying a lot of money for storing samples that they're never going to use. We're talking hundreds of thousands of dollars, okay? So Whitson PVT lets you keep track of all of these samples in storage, lets you do basic things like keep track of the costs, link it to any PVT samples that have been taken out of that sample in storage. So you can see if any of those have PVT experimental data, that you might just want to flush that sample and say, I have all the data I'm going to need. And you can also keep track of the quality of that sample, okay? The next part is estimating our compositions, right? Reservoir compositions are not measured directly. They are calculated by the lab, okay? And it goes through a process like this. You flash it to surface conditions, you get a flash gas, you get a flashed oil, and then that flash gas is measured through something that's called a GC. You get a molar composition for that. You get your flashed oil. That's also measured through a GC. You get a mass composition for that. You have to convert it from mass to mole. And that's the whole process. It's complicated, but that's what happens. So all the compositions you use for your describing your reservoir fluid have gone through this complicated process. You can keep track of that in Whitson PVT. Most PVT softwares, you can only put in the reservoir composition, which has uncertainty. Then you have PVT experiments. Those can also be data-based. Let's say this is an oil sample. We might do a CCE and a DLE. You know, unless you're Ed or me, you don't like the DLEs for some reason. So you might do something else. And so basically, Whitson PVT is a platform where you can create a digital database of all your available PVT data. You can do automatic QCs of that data, and you can easily kind of cross-plot the data in a field or in a basin on top of each other to spot outlier data or different trends. So following Matthias's demand here, I'm just showcasing a little bit of what the software looks like. This is not Whitson Plus, it just looks like it. It's Whitson PVT. And you can see here, you can go to the samples overview. You have all your different wells and all the attached PVT samples there. You can look at the QC. You can go into a given sample and look at its metadata, the compositional data. You can zoom into any one of these plots here. Then you can also look at the PVT experimental data. You can plot, for example, the single-phase densities, or you can go look at your multi-stage separator test, and you can look at the gas being released and so on and so forth. Automatic QC is done on all these experiments. You put them in, you just hit run, and you can download that, put it in a PowerPoint, impress your boss, get a paycheck bump. You can also do cross plots. So I just selected all the samples and all the wells that we have for Duvernay, and I just want to look at what does my liquid relative volume look like for all of them. And I can see here that I got some gas condensates, some are lean, some are rich, and I have some volatile oils as well. And then I can go directly to the data through that plot, just control click, and then I'm back to where I started. Okay, so a question I get asked after showing this is Whitson PVT just a database for PVT, and here's why. Okay, if we have a database for PVT, that is the first step to seamlessly putting that data into a fluid model development procedure, like we did for all of the JIPs. And we can very easily create equations of state models that describe these fluids. And then we can take that detailed equation of state model, which you have access through the JIPs, for example, and you can create lumped equation of state models if you're going to be doing compositional reservoir simulation, or you can generate black hole tables as well. And you might say, wow, that's cool. Is there anything else we can do? All right, is it just another software that lets you make equations of states and black hole tables? No, in fact, there are more things that you can do here. Once you have the data, once you have the models, you can do a bunch of calculations as well. You can do flash calculations, generate phase envelopes. You can actually generate synthetic PVT experimental data. So if you're exploring in new wells and you don't have time to wait for the lab to calculate the multi-stage separator test for that fluid sample, you can put in the composition into Whitson PVT, and it'll generate that PVT experimental data. And then fluid model validation, all right? Same thing goes in. If you get a new sample with a bunch of new PVT experiments, and you don't trust the people at Whitson who made your equation of state, and you want to use that equation of state to validate that it can still predict those new samples, maybe from a slightly different area, plug it into Whitson PVT, run the calculation, and it'll tell you, yes, you can predict it, or no, it cannot. And with that, there are some things that are going to be coming up, which are very interesting. We're going to be doing fluid initialization here. Ravi from Oxy was making fun of me because we didn't already have this. Looking at our compositional variation with depth is something we're going to be doing, and kind of doing it in a nice and visual way. Flow assurance things like wax and asphaltene is also going to be part of it. And then also having a visual map of where all your PVT data is also going to be coming now, hopefully before New Year's as well. And this is just part of the things that are going to be coming in the software, but we're always driven by what you guys, the operators, need. And so this might, change a little bit, and there might be other kind of big features that are going to be coming based on the feedback we get from you all. All right, it wasn't too bad. We got through it. Yeah, I think that's it for me, and I'll open up for questions here. Anybody dare?
Since this was more of a information part, I think we can allow for not having any questions there. But if you guys want to know any more information, contact Marcus on that for sure.
All right.
So thanks, Marcus.
We're going to be on the PVT, and now we got warmed up a little bit on the PVT part. So we're going to go from kind of like basic PVT, if you like, day-to-day PVT, to what I would call exotic PVT. I don't know if that's the right word. And I'm not going to do any bad play on words there with exotic and Exxon Mobil, but my very good friend Ed is going to present on this. It's I think the experiment had never been done before, really before that was done by Ed and his colleagues at Exxon Mobil. Ed is a very what can I say? He's a very humble guy, so he won't tell this to you himself, but he literally built the Exxon PVT lab, of course with a team, but from nothing. So very, very impressive background when it comes to PVT, both from a lab perspective, but also when it comes to the modeling piece. So with that very humble introduction, I'm gonna leave you the stage, Ed.
All righty, thank you for those kind words, Matthias. Whenever I talk to people that start startup companies, like CEOs, they always say if they knew what they were getting into, they'd never do it. I think the one lesson I've learned from building a PVT lab from scratch is if I knew what I was getting into, I'm not sure I would have done it as well. It's a similar experience there. But one of the things, as Matthias said, is that one of the things that we have done with our PVT lab is, what was it, 2021 timeframe or so? There was a paper, Matthias Curtis was on it. It was presented at ERTech, and that they called the gas huff-and-puff PVT experiment. A lot of the phase behavior experiments that we measure in the lab are not really designed for huff-and-puff. When we're thinking about later in life, you get done, you guys have done all your great work with your DCA, your RTA, and all your other models, but when we get done, you realize that we're leaving, well over 85%, over 90% of the oil still in the ground. And the question is, what's next? We don't want to leave that much. And so gas huff and puff, at least within ExxonMobil, is one of the leading concepts. And without having any of in order to model that, of course, we need to have good phase behavior data in order to make any reservoir models. So reached out to Curtis. We thought, well, let's jump in this together. He mentioned that nobody had ever done this, and we decided we have a PVT lab. Let's go. So what I'm going to talk about today is why the PVT huff and puff experiment, what it is, what it tells us, and how we can use it to help us design projects. So Hoffman and others have done published reservoir modeling studies on the mechanisms present in huff and puff projects, and a few of the key ones that come out include swelling. That's just mixing of the gas and oil, increasing the volume, providing some reservoir energy. Viscosity reduction, which is a more minor one, with these viscosities already being low in uncon reservoirs. That one tends to be a little bit more minor. Vaporization can play a role where lighter components within the oil will vaporize into the injected gas, and then pressure support, just you're increasing the pressure. So having accurate fluid property input into our EOS, we only get one chance to do a huff and puff project, lots of variables we can pick, so we use modeling in order to be able to do our experiments in the computer, and we need to have accurate fluid property data in that model. And so what we had done previously with some samples where we were looking at this, we had already done swelling tests, viscosity measurements on both the original and the swollen fluids, and really pressure support's probably more related to special core analysis and just transport of the gas into the rock. But the one thing we hadn't done was the gas huff and puff experiment, and so in order to quantify vaporization, and so off we went. And so the next thing is what is the gas huff and puff experiment? Well, it's a simple 3-step experiment, and I'll walk through the first step. So the first step is to mimic the primary production. That's what when we're doing a huff and puff, we don't want to do it on a brand new well. I know, having attended ERTEC the last couple of years, there's some debate about how many years you want to wait, but the first step is always going to be primary depletion. Go get that present value that a new well offers very quickly. So the first step we do is a constant volume depletion step. Was what was recommended by Curtis, and so we do it in a 2-step process to get us down to our initial pressure, and that's going to be the bottom hole pressure that you think your well is going to be at when you're ready to start huffing. The second step, at this point, it kind of splits depending on where you are in terms of your pressure relative to your saturation pressure. If your maximum pressure that you're going to inject gas to, if that's still above your saturation pressure, then you can see, where's the laser? Here it is. Sorry for those of you on that side. If your maximum pressure is above your saturation pressure, you're still going to have, after you're finished with your injection, you're still going to have a single phase oil. If your maximum pressure is below your saturation pressure, then you'll have a two phase system in your PVT cell, and that's going to be step 2, is your constant volume injection step. Your third step is going to be mimicking your puff cycle or your production, and that's going to be pretty standard constant volume depletion for those of you that are familiar with that from condensate experiments. And so once again, it works a little bit different depending on if your maximum pressure that you're going to be pressuring your reservoir up to is above or below your saturation pressure. If you're above your saturation pressure, your first step will be to do a constant volume depletion where you increase your volume and then you remove oil to get back to your original volume, and then you're trying to target, in this case, getting down to your saturation pressure, and that's do your best guess there. And then the second step is you increase your cell volume to the point where you get to your minimum pressure, bottom hole pressure that you're looking to go to. And since you're already starting that step at saturation pressure, you're going to be evolving gas, and then you remove the gas. If your maximum pressure is already below your saturation pressure, it looks very similar. The only thing is this first step is that you'll be removing gas on the first step instead of removing oil. This represents one cycle of your huff-and-puff experiment. You repeat cycles 2 and 3 for additional cycles. And you can do really as many cycles as you want. I believe we did 4 or 5 ourselves. You can also do additional steps here. I've written this for 2 steps, and that's what Curtis recommended, but there's no reason if you wanted to do additional steps, you could. It just gets a little bit more time and costly. Also, keeping track of the material balance from a technical perspective, you're going to have so many gases coming out. You do need to make all those measurements and keep track of the composition throughout all this in order to be able to model this with your equation of state. And so the more steps you have, the bigger challenge that becomes. So what's the huff-and-puff PVT experiment tell us? It tells you a lot. Probably the most important thing, you'll see the slide again actually, probably the most important thing and what really has gotten a lot of attention within ExxonMobil is it tells us it gives us a limit. It's a thermodynamic limit of recovery based on huff-and-puff recovery processes. It's a limit that's a function of 4 things. One is the hydrocarbon, hopefully oil composition that you charge your cell with, the injection gas that you choose, what temperature you're running this at, your reservoir temperature, and then the difference between your maximum and minimum. So that's one key thing, and because if you probably the first step that you want to do if you're huff-and-puff, you have an oil, you have a gas, you probably want to know, well, if I can't make money at the thermodynamic limit, I'm certainly not going to beat it. So you're going to want to probably make some different design choices. Other things, so the first bullet up there, that's just the thermodynamic limit. The other thing that other things that it tells us is the utilization of the injection gas. And basically how within ExxonMobil, how we define incremental oil is it's basically the number of barrels of incremental oil that you're recovering per million standard cubic feet of gas that you are injecting. And you can actually, if your initial saturation pressure is below your maximum injection pressure, you can actually quantify utilization for your swelling portion. If you have a single phase, if that first step is single phase, then there's no vaporization because there's no gas. It becomes a single phase. So that that the recovery is entirely through swelling, and then you can calculate those utilizations above and below saturation for either swelling or vaporization. You can actually calculate a recovery factor based on the amount of oil that you recover from the PVT cell and comparing it to what you start. And then finally, you're able to track saturation pressure as you go through the experiment, which will be useful when you're going and doing your EOS modeling. So how do I use this experiment? Again, this is a beautiful, exotic, to use Matthias's word, experiment, but ultimately we're not doing this to do interesting PVT measurements. We're ultimately using this to make an impact on our business. So I mentioned, obviously we're going to be using reservoir simulation as a primary tool to design EOS, EOR projects. And so the EOS needs to be tuned to experimental data. We need to make sure that we give this experiment some heavy weighting because that's what we're trying to simulate. So that's one of the big uses for this experiment. We can also examine the relative role of swelling versus vaporization, and it actually can give insights. If you have the option of being able to tune your injection composition, you can see maximize that recovery. But of course, you have to balance that against the cost of the injectant if you want to start getting into more expensive injections. You can actually use this to inform how many cycles are going to provide economic uplift. Obviously, as you deplete the oil that's there, you're going to have less and less oil available in your cover, less and less. And so at some point, it's going to become non-economic. And you can use that in your simulations to try and estimate how many cycles you should be doing. And then finally, you can develop a more complete understanding of the recovery mechanisms from the huff-and-puff projects based on this experiment, and use it as a screening tool to decide where to do huff and puff in your field. So in summary, I said I was going to show this again. You are the key thing that you're going to be getting from this is understanding your limits and using it to inform your equation of state that you're going to be putting into your reservoir model, and understand if you can make an economic project out of these huff and puff projects. My last slide here is my obligatory Matthias Carlson slide from Whitson that he made me put in here. He probably knows ExxonMobil. In his presentation, he put up the kind of the logos of all 100 plus Whitson plus users. You'll notice one major was not there, and of course that's ExxonMobil. So I have no idea what this. I haven't ever had the pleasure, not my choice, but what this is basically the output from Whitson. Whitson plus from the of what you can get, and basically, tell me if I'm wrong. I think sorry. This is the cumulative recovery. This is utilization, I believe, as a function of the number of cycles. So you can see how, like I said, you're probably going to see a decreasing trend with the utilization of your injected gas. At some point, there's going to be an economic cutoff. Right here is your saturation pressure. Your saturation pressure. You can watch how it increases throughout the experiment. And then we have your recovery here in the lower right-hand side as a function of cycles. And then finally your mixing uplift, relative mixing uplift. Is that due to swelling, or is that due to the vaporization, Matthias? Yeah. Okay. So what Matthias said is basically this is due to the mixing or the swelling, and then if it's at 0%, it's 100% vaporization, and then in between you can calculate it. And that is all I had.
The only other PVT guy here, well, except for Najee here.
Yeah, I was going to say Najee.
Yeah, I'm just joking.
Or y'all.
I was just wondering on the procedure, like the lab procedure, what part of it, from your experience, do you think adds the most to the uncertainty of the results? I mean, you mentioned the material balance. The more steps you do, the more complicated it is. Did you see something in the implementation of this where you're like, oh, well, that might mess things up?
The hardest part of this is the material balance. You've got so many compositions that you're measuring throughout all this, making sure that you have very high quality compositional data, and that you're getting good measurements of your volumes as you're displacing them out of the PVT cell is going to be is where we found the most challenge, and where we have had the most discussions with your father there. And I will say this is the first time we've done this. I wouldn't say we necessarily, anytime you do anything for the first time, it's not going to be perfect. We've had a lot of learnings. I know we're planning to do more of these, but I would say the composition is really just being very, very careful, because material balance is important for any PVT experiment, but the fact that you've got so many injections and withdrawals from the PVT cell, far more than any other really PVT experiments, where you really have to be careful.
Ryan Nair from whitCon Technology. Thank you for the presentation. My question's around, so in this particular slide up here, this is the same experiment simulated using an equation state developed on standard PVT lab data.
Yep.
Can you give us a feel for how wrong this prediction would be compared to the experiment that you ran in the lab?
That's a great question. I actually was just earlier this week, I was emailing with Curtis about this. This, by the way, is not ExxonMobil data. This is a dummy experiment that Matthias just put on there. No way ExxonMobil would allow me to present any real data. The answer to your question is we are still working through that. I was a little surprised. Curtis said it is going to change things because Matthias actually put together one of these based on, just data that we had already had, everything but the PVT experiment. And I was emailing Curtis back and forth this week, and he said he expected it to change quite a bit. But we literally finished this experiment. The last bit of data was reported to the Whitson team just this past Friday, so we don't have results yet. So I don't know the answer quantitatively, but I was a little surprised when he said that he thought it was going to change things quite a bit. We are seeing some... It is clear that we're getting some mismatches on the oil recovery portion of it. What the EOS is predicting based on all the other data versus what we saw in the lab. The gas recovery has actually been pretty good. I've been actually extremely impressed how good the EOS is matching what we've been seeing out of the gas recovery. The oil, though, which is what we care most about, it is. It's going to take some work, and so I don't know. I don't know the answer yet, but Curtis did say he expects it to be quite a bit different, and that this experiment will add quite a bit of value because we are seeing a mismatch.
Yeah, guess we'll look forward to next year's presentation.
Thank you. That would require heaven and earth to make ExxonMobil allow me to show you the real data. Go ahead, Najee.
Thanks for the presentation. You called it a huff-and-puff experiment, but in this case, you showed the vaporization part of it in an actual reservoir. It's a combination of vaporization and condensation process, it's a combined process.
Agreed.
And in late 80s and early 90s, we used to do what's called a forward and backward multiple contact experiments. It's exactly the same. So it gives you some ability to handle it's another calibration point for the equation of state. Would you comment on if you use multiple contact experiment data versus this simple huff-and-puff, how much difference you see in terms of creating the simulator? This is a major difference. How do you explain that?
Yeah. Yep. Great question, Najee. I'll be perfectly honest. I'm going to. I don't know the answer, so I'm just going to start talking and speculating. Those forward and backward multi-contact experiments were designed more, I would say, probably in the conventional world for displacement processes. That is not what we have here in huff-and-puff. It's different. It's a huff-and-puff. It's not a displacement where you're going to have constantly fresh oil going and moving over. So my expectation is that it's going to be, especially based on what Curtis has mentioned, Curtis and my conversations over email the last couple of days, my guess is it would be quite a bit different, but unless we did I would think we'd probably have to do the experiment in the lab and go figure that out. But it's, I don't know, you might have more of a better feel than I do on that one, Najee, how different it would be. Can you, yeah.
Najee, so he said that multi-contact is kind of a huff-and-puff experiment. And, Najee, we're so good friends, so I'll just disagree a little bit with you there on that part. Because like in each of these cycles, you will capture vaporization if vaporization is relevant. The first few cycles, if you have a high maximum pressure, it might be just single phase mixing. But after, once your saturation pressures goes up, maybe every single step that you're moving during the production cycle might be two phases, and then you're capturing a lot of vaporization. Yeah. So that's the beautiful thing about this particular experiment, that it captures both sides of that story for the relevant reservoir fluid, injection, gas, and pressure cycling interval that Ed just went through. Question over there.
Hi, Roman from Texas A&M University. Well, these experiments are really good to quantify for huff-and-puff unconventional reservoir simulation, especially how PVT changes with time during these cycles. But have you gone a step ahead and tried to kind of look at the role in terms of quantify the role of diffusion when it comes to unconventional reservoirs, when the gas has to transport itself into the matrix?
I've gotten out on that one. I'm a PVT guy. Diffusion's a transport phenomenon.
Yeah, I mean, okay.
So no, I haven't. Oh, we do have people in ExxonMobil that look at diffusion, though.
Yeah,
I'm that guy.
I'm to just on, this captures the theoretical upper limit, and there has to be something that allows for that mixing. In the PVT cell, it's instantaneous diffusion. Yes. Right? It's instantaneous mixing. Yes. You won't have that in the fields. There needs to be some kind of mechanism that captures that. So if you run a simulation model and you get higher thermodynamic limit numbers than what you're getting in this experiments, something is off with your model. So that's something that the simulation crew at Exxon hopefully takes into account.
Yeah, that's right. And that's a key point. This is just a thermodynamic limit. Okay. You're not going to see this in the field. There's no rock in my PVT cell. I would never allow that. This is just the thermodynamic limit. So, and Matthias is right. I mean, you can have numerical dispersion in a simulator and get higher than thermodynamic limits, in which case that tells you need to go back to your model because there's a problem in the model.
Okay.
Or you did your PVT measurement wrong, but that never happens.
Okay, thank you.
That's excellent. So next one out in this session is my very good friend and business partner and colleague, and of course the COO of Whitson. Mo is one of these guys that often, he's kind of in the shadows, but for those who work inside of Whitson, they know that he's involved with everything, and he's the one that kind of keeps the day-to-day operations alive. And if there's nothing that he's not involved with on the inside, and doing a lot of these things without Mo would be absolutely impossible. And today he's going to go through a couple of tips, a couple of new things that we put into the software now in the last release. Again, maybe there's not many questions for it, it's more information, but I'll give you the stage then. Mo?
Thank you so much. Hope you can hear me in the back. Yes, very good. Yeah, so thanks for the kind introduction, Matthias. And I think I've done these types of presentations a couple of times now at previous whitcons or at least previous knowledge sharing sessions. And so what I'm going to try to do now is just show you a couple of tips. And as you see, the trend is that Matthias has been asking everyone to do what? Just put GIFs about Whitson Plus in their presentations. And so I'm going to do that just in 20 slides. So get ready. Not one slide. So the way I see it is challenge accepted. So we just had actually our biggest release ever, and that was 2 days ago. It's our biggest release ever. It has a bunch of things. I can't go through all of them now, but I'm going to go through some of them. But before I go through all the things that I'm going to show you, I have my colleagues at the back who are actually the superstars of all what you're going to see here. They are the development team that are sitting there. They take care of business every single day. So I want to thank you guys. You're amazing. That's why we're standing here. So the first thing I wanted to show you is that we have new mass upload interfaces. So you're used to seeing that you can go into Whitson Plus and you can mass upload, you can use the Excel template. You can go and pull data from drilling info. But then the interfaces that now I'm very excited about is that we have now the possibility of pulling Aries forecasts into Whitson Plus. What does that mean? That means that you can go into Aries, where you have your forecast from 2023 or from the previous quarter, and you can go and say, okay, I want to export those forecasts, and I want to tell Whitson Plus to take those and show me those forecasts directly without much effort. So you just pull an Aries AC economics file. You just have to link it to which prop nom in Aries corresponds to which property in Whitson Plus. Is it the well name? Is it the UWI or whatever it is? And then once you've done that, basically you're going to get your forecast, your Aries forecast directly loaded there, and you can do that for as many forecasts as you would like. What is the objective of this? It's because many people are basically using Whitson Plus for their forecast, and they want to compare against what they have been doing in the past. So you want to be able to load into Aries, and of course you're also able to export into Aries. So here I'm just showing that you have the Aries forecast there at the bottom, and then you can load them, toggle them on and off, and show them on the plot. The other interface that we have also is the Mosaic one, for mostly for our friends in Canada. It's kind of the same workflow, but now with Mosaic instead of with Aries. And also for our friends in Canada, we have now the reading of PAS files. I think they call them PAS. Maybe it's PAS files. And those are files that contain flowback data that I think are required by the AER in Canada. So basically every single well has that data, and they're very useful for doing well test analysis, like DFITs and CPG and DQI like we have now. Okay, so that's the first thing, talking about mass upload interfaces. And related to that, because we're talking about mass upload interfaces for DCA, then we also have now the biggest release that we've had when it comes to DCA, which is including a bunch of things, lots of, like Matthias likes to call them, bells and whistles. But the one thing that is very important is that we now have ratio forecasting. So you can do not only forecasts on the rates, but you can do the forecast on the ratios. And as you see there, we have also different segments, semi-log segment and power law segments for the ratio forecasting. And on the GIF, I'm trying to adjust the GOR forecast, and you'll see that my rates on the bottom should adjust, or my cumulatives on the bottom should adjust. For our friends that have been using the comparison plot a lot, we have very good news. And just a big disclaimer, by the way, the release that I'm talking about has not gone out to everyone. Some of you have seen it. Some of you have to wait maybe a couple of days to see it, but you'll see it soon. But for our friends that use the comparison plot a lot, we now have the possibility of saving plots. And what does that mean is that now when you go into the software, instead of seeing one comparison plot where you can change the templates, you can basically create a plot, save it, and you can share it with anyone you want, and it will be saved in this list here where you can go and access it later. The biggest difference there is that now the saved plot will also save your well selection, which before it didn't. So that's a very important thing. But that's not what I'm really the most excited about when it comes to comparison plot. The part that I'm really excited about is the performance of comparison plot. And for those of you who have not used it, this might not be very relevant, but for those who have used it, you know that it hasn't been the fastest. And now I just wanted to show you how quick you can do things, how responsive it is, how I can load. Here I'm loading 50 wells into the plot, changing the color of the plots, synchronizing the color between the 4 plots, all basically in a matter of seconds. Okay? So that's a big thing, thanks to our colleagues that they have implemented that. And also many of you have asked for the customization of the comparison plot because you don't like the choices that Matthias and I have made on axis sizes and font sizes, etc. So now you can move the legend wherever you would like. You have also the possibility of changing axis font size, tick font size, add grid lines, change the number notation from scientific to decimal points, etc. Okay, so that's hopefully something you'll find useful. The next one is something that our friend Greg from Cotera has already covered, which is the liquid loading dashboard. Something that we're very excited about and something that we want to build upon to create more dashboards like Greg was talking about. The one that we have now is the liquid loading one. We also have a custom dashboard, which you can access from the well overview going into the results page. And the custom dashboard, for those of you who have used the export from the well overview, where you select the wells and you click on export, and it basically throws out all the results from your analysis. It gives you the EORs from your DCA, it gives you the OIP from your flowing material balance, it gives you your numerical model outputs, and basically all the important outputs per well. Now you can see them in a dashboard that you can customize for your own sake. So that's a custom results dashboard. And now I would like to go into, for those that use the numerical model, I'd like to show you a new option that we've added that is called smart and custom time stepping. Okay, so usually this is a new dropdown that we've added where you have, instead of running every single time step in your simulation, now you have 2 new options. One is called smart, which will become the new default. Yeah, which will become the new default. And that the way I want to show you this is I want to show you what you're used to. So the simulations in Whitson Plus, if you're running a numerical model, they should take about a couple of seconds, maybe 10 seconds. So I'll show you this example. This is what you're used to. You click run, you wait for about 10 seconds, maybe 5 seconds, and then you get your results. This is with the regular time stepping. Now, if I go to smart time stepping, I click, and before I have time to tell you that I clicked, I should see the results. So it's a big improvement. And the big improvement here is when you want to run, excuse me, a bunch of models in parallel. So you want to run many models for probabilistics or for sensitivities. This is going to be a very important game changer for doing things faster. Here's just an example of the two cases, one side by side. The improvement should be approximately 2x, sometimes could be up to 10x, depending on your data set. Then we have, related also to the numerical model, we have introduced, from request from our friends at Chesapeake, we've introduced sensitivities with tornado chart. So what I do is that I go and select in sensitivities like I usually do. I go and select the variables that I would like to use. And with those variables, I just click on the tornado button there at the top, and I provide ranges for each of the variables, min and max, and I populate basically a matrix of cases. Here I'm just doing it with three variables. I populate a matrix of cases that will basically take my numerical model and will adjust those parameters and give me the output. So once I save, click run, it's going to run 6 numerical models for me. That's the output, and it gives me the tornado chart, which I can look at. That's thanks to our friends at Chesapeake for. That's on the numerical side. And on the general structure of the software, there's a very, very important addition that has been added, which is that now, whenever you copy a well, you have the option of linking the production data of that well to the source, and of linking the well border configurations also to the source. Why is this important? This is important for all of you who have the API set up with Whitson Plus, and you want to copy the well from the given project into another project. If you copied it before, what would happen is that the new well that you got into your new project would not get the updated data on a daily basis like you do through the API. With this, now you can link it and you can make sure that the data stays updated even if you copied the well. So everything stays connected. If you want, if you don't want, you just untick the box. So that's a new option there. And finally, we've implemented a new well test method, basically interference method, the Devon quantification of interference from our friends at Devon. I think Moin Al-Masoudi, he did the webinar with us on this technology. So we've implemented that, and you'll see that also under your well tests category. So with that, hopefully I didn't go over time. And thank you so much, everyone.
I had one question from Mo. What software did you use there? Okay, we're going to change gears a little bit. We're going to go to day-to-day usage of RTA. We have 3 different operators that's going to present very unique angles, or like the stuff that they're doing day-to-day in their day-to-day work in different basins, and they're doing, using very different parts of the workflow. And we're going to start with my good friend Deepak from EcoPatrol Permian, and he's going to show some of the work that he's doing there with the MFMB method, and essentially using a relative permeability-free type of forecasting method. So with that, I'm just going to give you the clicker.
Thank you, Matthias, and good afternoon, everyone. Can you hear me back there? Okay, perfect. So while I let you take in our really dazzling title slide, somewhat blinding, I'd say, but while I let you take in that, I want to say what I'm presenting today is some really, really basic stuff, and stuff that everybody should be doing on a regular basis. If you're already doing it, that's great. More power to you. If you're not, I hope that I can convince you to start doing it. So I want to start with a couple of quotes. The first one by Niels Bohr, who once famously said, prediction is very difficult, especially if it's about the future. The second one is attributed to a British economist by the name of Ronald Coase, who said, if you torture the data long enough, it will confess to anything. The relevance of this quote to these 2 quotes to a lot of us as reservoir engineers is that we are constantly navigating the realms of the unknown. That's one. Second, there's a tendency to overanalyze the data a lot of times, and a lot of times we end up confirming our own biases. So a way to mitigate either of these issues or both these issues is you want to approach a problem from multiple angles and try to get to the same answer with different approaches and look for convergence. And what I present today is a very basic approach to to do this. And so let's jump on. And so the objective is to demonstrate the application of the recovery factor approach in the Midland Basin. And for clarity, what I'm referring to is the workflow within Whitson for recovery factor analysis. So the agenda, I'll take you through a brief explanation of the approach, a basic workflow, show you an example of this application in a few wells in a few older wells in the Midland Basin, and then finally, just how do you take this and apply it to a set of brand new wells, which is always the question. On day one, your managers want your EUR, and so how can you probably get to that point? So the theory has been discussed in great detail in previous presentations. Our friends from Coterra have gone through this in a lot of detail. I'm not going to touch on it, but the simple concept here is your recovery factors are dependent on your relative permeability and your fluid properties. But if you are somehow able to forecast your producing ratios or know what your producing ratios are going to be at abandonment, then you can avoid relative permeability, which is a highly uncertain parameter, as Matthias was talking about earlier. So that's the simple concept. The equation on the right side is a very, very simplified material balance equation for saturated solution gas-drive reservoir. So what is the focus? The focus then becomes forecasting your producing ratios. And the framework itself is really simple, and that's why it works. The framework is that your recovery factors are inversely proportional to your cumulative producing ratios at abandonment. And what it means is if you can keep more of your gas inside the reservoir, then your recovery factors are going to be higher. So that's how it works. So the workflow, very simple again. The key inputs are your recovery factors, your producing ratios at abandonment and the abandonment pressure. And if you have that, you get your recovery factor. You can combine that with your flowing material balance, your pore volume, and hence the oil in place from flowing material balance. And that's going to give you your EUR. So that's the simplistic explanation. So what I like to do is start with an analysis of the offset wells, that have a lot of production data that gives you a sense of what the producing ratios would look like later in life. You start with that, move on to your flowing material balance that gives you your pore volume are in place, combine the two, and you have your recovery factor from your recovery factor analysis, you combine the two and you get your EUR. So very simplistic stuff, nothing groundbreaking. I've looked at numerous wells, and there's a few things that in the process that has worked for me and made this a little easier. So the first one is, prior to looking at any of your new wells, our tendency is always to, hey, I've got this well, I'm going to plug it in and start going down the line. But prior to doing that, take a look at offset wells. Look at the cumulative producing ratios in offset wells. Proprietary data works best for this, but if you don't have that, public data works great also to get a sense of that. So on the right side here, the first plot is about 37 wells, all from within a 2-mile radius, producing from the same bench, and you can see the cumulative GOR over time. And so tip number 2 is try to limit your well set that you're looking to that are closely aligned in spacing and completion design to the wells you're going to look for. Why? Because these two parameters tend to influence your contacted pore volume ultimately, and they influence how your pressure declines and how your GOR evolves. So I found that it's always easier for me to look at the GOR when I filter my data set. So that's the second plot. It's filtered down to about 5 wells, all producing from the same DSU, consistent spacing, and completion design. You can see that the spread in GOR is now a lot lower, and it's better behaved. Third one, and this is something that everybody knows, but it's hard to follow with companies wanting a single answer, is consider a range of forecasts. And the reason you want to do that is because that there isn't a single answer. It's best to acknowledge that and try to come up with a range of forecasts. Okay, so let's jump to application in the Midland Basin. I want to talk about 25 wells that I looked at. This is 5 different DSUs, all right next to each other, contiguous DSUs. The wells are all producing from the same bench. They have the same completion design, same well spacing, which makes it phenomenal for this kind of a comparative analysis. The only difference is the wells were landed in 2 separate landing points, and you see that in the colors. You'll see the similar colors repeated throughout this presentation. There's a lower landing and an upper landing in pink and blue. So one of their contexts is that these wells were all developed simultaneously, more or less. So there's not depletion, any of those things going on, again, which makes it all great for this analysis. So I took all of these wells into Whitson and forecasted their GOR. So here is one such example of a forecast. The plot on the left side is the oil to gas ratio against bottom hole pressure. The plot on the right side is the same thing converted to GOR. A lot of us for oil wells are used to looking at GOR, so that's just a converted plot, so it's nothing different against bottom hole pressure also. So here I like to do a couple of cases. I call it a base case and an optimistic case. The base case is very simple. It's just your producing GOR extrapolated, just as it is. Your optimistic case just assumes that the GOR becomes flat at your final data point that you have right there. So this optimistic case is pretty much your best case scenario for the well from a GOR evolution perspective. It's not going to get much better than this. And then, there's always a question of, okay, what about pessimistic cases? I don't normally like to do it because there's too many degrees of freedom with the pessimistic case. And a lot of times what I found is that it's too conservative and often not very realistic. So that said, let's look at the results. So I've got 3 plots here. The first one on the left is a distribution of pore volumes from flowing material balance. The second one and the third one are the base case and the optimistic case recovery factors computed from the recovery factor analysis that I talked about. Within the plots, again, the blue and the pink colors are the the lower and the upper landed wells, and then you will see dotted lines, and those dotted lines are the average of those values for that average of the distribution for each of the different landings. So there's a blue line and a pink line. So first takeaway, the plot on the left, immediately you'll notice that a lot of the pink points are plotting at the bottom of the distribution. The blue points are at the top of the distribution. This is also seen in the spread. So the lower landing is obviously not looking as good from a pore volume perspective. But when you look at the recovery factor plots, the second and third, you look at the blue and the pink dotted lines, they're almost right next to each other. Why? Because the recovery factor is a function of your fluid property and your producing ratios. And you noticed that early on that all those GORs were all like tightly clustered together. So the recovery factors are pretty much the same. Another thing you'll notice is in the second and third plots, the base case recovery factor and the optimistic case recovery factor are more or less the same. So the question is, why did we do it? And why are they so close to each other? The reason is, the wells were all fairly close to abandonment. Look, the objective is to look at older wells and understand, how they produce. And so in this case, since they were so close to abandonment, there's not like a huge range in the production. So now we have our recovery factors. We have our pore volume from flowing material balance and the oil in place because the geologist is giving you a saturation, water saturation. So you have your oil in place. So how do you take this? So you've got these two now. The product of these two is going to give you your EUR, right? So that's what I've plotted here. You've got your EUR. There's 2 plots again. The first plot on the left is the base case. The second plot is the optimistic case. And I've plotted both of these against a more traditional approach like DCA, which is what we regularly tend to do on a day-to-day basis. So I plotted them. So again, there's the blue and the pink dots. The key takeaway on this is, number one, there's excellent alignment between DCA and the recovery factor analysis approach. And there's probably some scatter, a little bit of difference, but any of that difference is all within 10%, and that's well within the margin of error for each of these approaches. So this is a phenomenal thing. I mean, you've taken 2 completely different approaches, and your EURs match up. Now, again, there's always the caveat that these wells are so close to abandonment that you know your producing fluid ratios really well, and so you would expect them to match pretty well if they're done consistently. So then it comes to the question of how do you take this and move it to a set of brand new wells that have very little data. So that's the slide. The context here is that we drilled 5 new wells in the immediate vicinity of the 5 separate DSUs that I showed in the previous slides. So these wells were drilled with the same spacing, same completion design. The only change that we made here was that the lower landing was eliminated. We pushed all the wells to the upper landing, and we saw that the lower landing was really not looking that great, so we pushed everything to the upper landing. So the first plot on the left side, that shows a comparison, straight up comparison of OGR versus producing days. So you can see that the wells I'm showing just have about 90 days of data. And here you can see that the initial GORs, or OGRs if you want to call it that, in this plot, the initial OGR is pretty much in line with the rest of the historical wells that we talked about. And the trend is also more or less the same, okay? So the second plot is directly an output from Whitson Plus. Here I've shown you the extrapolation of the producing ratios that I did within Whitson Plus. And here all the dots are the 25 wells, the historical wells, and then the lines, the solid lines, are the new wells. At the end here, I've shown both the base case and the optimistic case. The optimistic case is in the dotted line. It's kind of hard to see there, but it's there. So one point I want to make here is that most of these new wells roughly had, on average, about 2,500 psi. That was the flowing bottom hole pressure when I did the forecast. And so I had to extrapolate from 2,500 down to 500 psi. And the way you do it is you've got this as a guide because you've looked at a bunch of the older wells, right? And the third plot here, that's the output. So once you do this plot, you're able to go on Whitson and look at this. This is the output, and that's your cumulative GOR versus your cumulative oil. And this parameter is what you saw in the earlier material balance equation. That's what drives your recovery factor. So here you can see that the cumulative GOR for both the base case in red, the optimistic case in green, they're pretty much in line with the older wells, and that is the intended outcome. You want it to be like that because that's what you're trying to model. Okay, so having said that, so now you've got your recovery factor analysis done. So let's look at the similar plots again. So in this case, there's 4 plots on this page. The first one is again, the pore volume from flowing material balance, and then the second and third plots of the base case and the optimistic case recovery factors, and the last one again is the EUR. Okay, so on the first plot, immediately, one of the key takeaways is you'll see that the red dots are now plotting at the top of the distribution, and there's separation between the gray line, which is the historical wells, and the red line, which is the new wells. And again, the reason for that is I told you we looked at the older wells and moved the landing. This actually worked out pretty well for us. So that's the primary reason. But given that your producing ratios for the new wells are pretty much in line with the older wells, the recovery factors are almost exactly the same in both cases, both the base case and the optimistic case. You can see that those lines are pretty much in line with each other, and the red dots are distributed evenly among the gray dots. So that's great. The process works. So you've got your pore volume and your oil in place. Again, you've got your recovery factor. Multiply that, you get your EUR. In this case, you'll see that the EUR for the older wells is some at 37 barrels per foot. This is at 45 barrels per foot, and this is great. And this is commensurate with the increase in pore volume, which is what you'd expect because your recovery factors are the same. So why is this important that you're able to estimate this EUR? Because these wells have 90 days of data. You try to do a DCA on this, you're either going to end up too high or too low. You're not going to get the right answer at that point. There are other approaches you can use, but the fact that you're able to take a very simple recovery factor analysis, which is also a solid basis, and get to a reasonable answer within 90 days, I think that's really valuable. So that's the strength and advantage of a process like this. So brings us to our final slide. So some key takeaways is we looked at the recovery factor approach. It's simple, It is, based on, it's got a solid grounding on physics, and we're able to use this to come up with EURs early on, and it compares really well with your traditional DCA. So that's one. We looked at some tips for GOR forecasting, or OGR forecasting, how we want to call it, and then we're able to take this analysis on older wells, apply it to new wells, and again come up with something solid in a very short amount of time. So the closing statement is, it's a great approach, it's simple, it's reliable, it should be a part of your toolkit among all the other approaches you use to come up with DCA, EURs, be it DCA or numerical modeling or anything else. If you can add this to your toolkit, I think you'd be all the more powerful for doing that. And that's it.
Very good. Nice presentation. Thank you.
Thank you.
Just to, since you compared the results that you got from the material balance approach with the DCA, have you compared the same thing but with RTA or either numerical simulation, or you haven't done that?
I have. I mean, when you talk about RTA, there's a couple of steps to it. Again, let's say analytical RTA, you're talking about your A-root K or your SRV from that process. You take that, somehow you have to correlate that to your EUR. And then, the second step is, how does that compare to this? So in reality, for a lot of wells, I find that, most of these approaches tend to converge, and you are looking for that convergence. And, if there's a lot of scatter and if there's a lot of, spread between the data, then you want to see, why is it happening? And, why is this approach so much different from the other? But in the grand scheme of things, if you've got the right amount of data, like these wells, for example, I had a lot of shut-in data on these wells. So my flowing material balance is a lot more reliable than a case where, you wouldn't have any shut-in data. So, does it mean that if your well number is not converging, is it because my FMB is too low? And it might happen to go up over time. So those are some of the things, and if they don't converge, that's what you need to think about. But yeah, generally I've seen pretty good convergence from different approaches.
Excellent. And now the next presenter has the same name that I use when I go to Starbucks. I've given up trying to give them the name Matthias. So my Starbucks name is Matt, M-A-T-T. And Matt is a very good friend of ours from Oklahoma City, and he's going to talk about using RTA in the MidCon. So that's, I personally call that the Anadarko Basin, God's country.
All right. See a lot of familiar faces in the room. For those that don't know me, Matt Padgham. I'm with Citizen Energy. We're headquartered out of Tulsa, but a lot of folks in Oklahoma City as well. We've been active all over the MidCon for about 10 years. I've only been with the company a couple of years. I think the last presenter introed with it was going to be fairly elementary. I think I will drop the bar yet again, and this is fairly entry level, but kind of walk through a case study for us. So our typical approach is, when I came on to Citizen a couple years ago, we onboarded Whitson at the same time and spent the time up front getting our flow back and daily data into the platform. Little bit of labor up front, but has saved a tremendous amount of time on the back end. We're a relatively small shop, private equity backed, really the only true functioning day-to-day reservoir engineer is myself, and we have about 700 wells. So it's a little bit of a bear at times, but having the data at your fingertips has been tremendous value. Our typical workflow is, not too dissimilar from other people that have talked today. Bottom hole pressures calculated and QC'd, looking at flow back on new wells, RTA and flowing material balance on wells of interest. I won't say every well. We haven't looked at all 700 of our wells to date. Many of those have been acquired over time. But the big thing for us is just getting a simple model that works in any given area. Its geology is equivalent to the RTA, and RTA generally aligns with our reserves view and what we're putting out there for our board or elsewhere. So looking at, as Matthias said, the Anadarko Basin, not just the MidCon, but we're specifically focused in the Anadarko Basin there in western Oklahoma. Really, we've spanned the gamut on TVD and GOR, anywhere from, the black points there on the top, GOR sub 2000, all the way to dry gas, and then the same thing on TVD. specific kind of case study today is looking in the red circles on the map there, which is kind of the dry gas extension of the stack. And so it's relatively deep, 13 to 15,000 feet, overpressured dry gas that, is gathered and delivered into a residue pipeline. For us, typical development here has been 10,000 foot laterals, 2,000 pounds per foot, and 50 to 60 barrels per foot. And kind of beyond that, it's an area that was drilled historically for other zones. For us, we're drilling the Mississippian, and it's really, HBPing acreage, kind of single two well pairs, so not a lot of full section development just yet. So looking into a typical well, so this is an 8,500 foot lateral, just under 14,000 feet TVD and nearly 10,000 pounds of pressure. And you see an IP on this one. I can work this. Around 8 million a day. So that's a fairly typical well. This is a very choke decline early on. We're fairly aggressive in our choke management in terms of keeping things choked back, that is. This well did coincide with COVID, so you see a choke change here. And rates drop in line with that. But this is a typical well. I'll show on the next slide a recent example. So this was a well brought online earlier this year. Gas prices were not great at the time, still recovering. But the decision was made when we brought this well online of let's just hold out and see where gas prices go and hope for a cold winter. So in this example, we held the choke constant at a 12/64. And so, this is a 200-day scale here, slowly building up to, still under 3 million a day, but 7,000 pounds of bottom hole pressure. And so, the big question, from management, board, et cetera, is how's this well doing? Did we do a completion test here? Did we try anything? And now I'm waiting a year or more for results. And I guess back on the previous slide, just to highlight, even on this example, which is kind of the typical well, if you were just running with straight decline curve analysis, when would you have confidence in that forecast? Is it a year, 18 months, et cetera? And I would argue it'd probably be at least a year, and then I think most people would generally be wrong. So taking our choked example, that's where we kind of get into, having that simple model for an area. Geology ties to RTA, ties to reserves. So here's our typical well in RTA. I realize this is probably very small in the back there, but you have kind of in the pressure normalized rate plot here in the bottom left, you have a period that's a half slope or linear flow, and then fitting that same period in the square root of time plot, you come up with an LFP per foot of around 12.6, and for us that equates to an EUR of around 1.8 BCF per thousand. And I'll show on the following slide how I get there. But we're basically, using wells like this with longer histories, kind of more mature tests to understand that choked example. So here's, a sampling of the dry gas wells in the area, RTA, y-axis LFP per foot of lateral, and then the x-axis is just our EUR per foot from our DCA or Aries look. And, generally not the best correlation, admittedly, this would generally be tighter. I would say I haven't culled any data points out of this sample, and there's, a few that probably should be culled for various reasons. But, here's our typical well, LFP of around 13, EUR per foot of around 1.8 BCF per thousand. So now if we look at that same approach on our choked example, so this well has a little bit of a different profile on the pressure normalized rate, right? You have a long period that's a quarter slope here, some sort of choked restricted flow. I will say we did have tracer on this well, so we were watching the tracer, to make sure that we were seeing the full lateral contribution. I think good rule of thumb is if you have inclining rates, always be suspicious if you're seeing a full reservoir response at that point in time, or if you're just seeing a portion of the lateral. For this, then, transitions to a half slope there at the end. So we have a short duration where we can, look at what that LFP per foot would be on this well in the square root of time plot. And in this case, really just jumping back to the previous plot is, where does that LFP of 6 plot? And it's 1.1. And you say, wow, you've been drilling this area for 5 years and your wells are getting worse. And so I think that circles back to the predictive model, having something that you can tie back to in terms of geology and well performance. So in this area, the plot for us has kind of become this gross height versus LFP per foot on the y-axis, and it's gross height seems obvious. Anybody would have that and use that, and you're like, why wouldn't you use gas in place, or why wouldn't you use VH, or any number of calculated gas in place? In this example, unfortunately, what we have is kind of gross height. So this is an area that was developed horizontally for Woodford with very few pilot holes. And so even if you were to, do the most robust petrophysical or geologic assessment, your control points are 6, 7, 8 miles apart. So you would have very little confidence, I think, in that model, even at the end of the day. So for us, we've kind of rooted, kind of in the simplest answer possible, which is just gross height. And then, there's other nuances that we've noticed as well. And so we have a couple different proprietary iterations. So sympathize with my friend at Exxon there that even if in the private equity world, you can't share everything. So this is a somewhat redacted, but they were willing to share this. So kind of to summarize, I think jump into the bottom bullet here is, maybe a little bit of inspiration. So even if you're in an area where you don't have a robust subsurface model, or you're dealing with, non-operated data, still do the work, try to throw as many things at the wall in terms of analytics to say what makes my wells tick. And so in this, I think we were somewhat skeptical that gross height really mattered in this area. Kind of back to that previous plot. I can attest that the gross height's not changing that significantly. So it's not just gross height, there's other things, but it's been at least a decent predictor. And then, I think there's been a lot of non-paid plugs for Whitson today, and I'll attest that, the API integration has been a huge time saver for us. I think we have many examples now of Whitson serving as a shared platform for our production and reservoir team to kind of have a cohesive look at the data and compare and contrast, certainly during flowback and other times. And then lastly, I think it's fairly obvious, just the ability to use RTA to normalize away differences in choke, differences in strategy within a company over time or between companies has been extremely valuable. So that's all I had. I promised it'd be simple, and I tried to be under 15 minutes. So.
That was really good presentation. Thanks for sharing. I remember once I worked with lines, and you see other signature by leading flow really nicely. So I think you leveraged that. So my question is next, is Matt or Matt's team using this analysis to tweak some completion knobs, perhaps to optimize on certain metrics?
So for us specifically in this, yes, we do, but I would say in this example, I kind of cherry picked it just because it's an area where we've been trying to basically drill and hold the acreage. We haven't moved into full section development. So this has been a very cookie cutter completion. Just all the wells are very, very similar.
Excellent. It's always good to see some Oklahoma wells, Curtis Whitson, for those who don't know, he's from Oklahoma. So I'm sure he also loves the Oklahoma wells as well. They're beautiful. One OKC, or I guess, Oklahoma company, at least to another. We're going to get our friends from Devon with John here to present on some work in the Permian. It's going to be really cool. And the stage is yours.
Hey, thanks, Craig. Okay. Hello, everybody. Like Matthias said, I'm John Dwyer. I'm a reservoir engineer in the Delaware Basin at Devon Energy. And today what I'm going to do is go through some rate transient analysis and numerical models and kind of show how we use that to do spacing delineation estimates in uncertain landing zones when we have highly complex developments. So starter off, I want to give a kind of an idea of the scale that I'm talking about here. So on your left is it's a cartoon gun barrel of a recent development that me and my team did. So you can see just off the top, it's highly complex. We have 6 landing zones, 18 planned wells, as you can see in the gray and the green. And then amongst those 18 wells, we had 14 existing wells of various frac vintages and various depletion grade. And it's
it's a lot. And of course, everybody wants to be able to estimate how all those wells are going to do. And at any given time, some of those landing zones are in development mode. Others are in appraisal, where you're testing for the very first time, like a parent well, and others are in the spacing delineation mode. So, you look at this and go, well, why would you do this, John? That seems stupid. Why don't you do this simpler? And the quick answer is like, well, there's a lot of factors here. We have a lot of corporate production targets we have to hit. We have we want to avoid any depletion that we could walk ourselves into. So we might take a little more risk on the spacing end to avoid the depletion overprint later. And of course, there's the question of risk tolerance, and that can ebb and flow given how things are looking. And so, on that, let's talk about risk real quickly. Clearly, one of the downsides of the highly complex development is your risks are compounding. And so it's really important for us to do our best to contextualize that risk. So, you can look to the right here and you see a distribution here. This is of a different development that we did recently, and you can see the NPV10 here. This is a Monte Carlo simulation for the development. The P50 is like 158 million, and then the middle 80 is like, well, anywhere from 135 to 175. Yeah, so these complex developments, you just start increasing the realm of possibilities. And so we have to do a lot of tricks. We got to have a really large tool set so that we can do, with our best effort, a good estimate on each one of the wells that we're going to go ahead and plan. And so again, today what I'm going to do is I'm going to focus on providing spacing sensitivities for wells that are in the development like this, but landed in an appraisal zone. So maybe you have a parent well and you're going to move right into a spacing delineation test. Okay, so what are we going to do? First thing we're going to do is we're going to find a parent well to tether this analysis. So here I just chose a well at random, literally had a list of parent wells and just had my computer randomly generate a number. And that's the well we're doing today. In this pretend scenario, I'm going to take this well and pretend that I'm developing somewhere in the south of my acreage, and we're going to decide what kind of a spacing test we're going to do here. Considerations for the parent well are, obviously, you want to have the same landing zone and or petrophysical properties to the best of your ability. And then you want to make sure your fluid composition is similar. So initial GOR is the easy way, but of course you want to use the Whitson virtual PVT to get a good grasp on if you're in the zone. And then after that, spacing situation, you want it to be apparent, but of course there's always something around. It's the Delaware. And then lower on the list is depletion situation, frac vintage, drawdown strategy, production data quality. You want to hit them all. Sometimes you don't get them all. Okay. So once we've picked the well, you're going to go through the bottom hole pressure corrections and all the PVT stuff, but I'm going to skip that and go right into the analytical rate transient analysis. So now, those who've used Whitson a lot, you can see that in the analytical RTA, they kind of have two options. One is the more traditional view, and the other is the fractional RTA or Acuna fit. I actually like to start at the Acuna fit, and the reason why is because it's really easy to get a quick snapshot of how many flow regimes have I had, and start to first level speculate on what those flow regimes mean. So hilariously enough, this random well I picked is a weird one, but that's how life goes. So we're going to use the weird one. First things first, you can see that I've labeled 4 proposed flow regimes here. My very first one looks like a radial flow. So the Acuna fit gave me a delta value that would imply that we are far below bilinear flow. And in the radial flow, the way that I interpret that is, well, we're not seeing a boundary, we're not seeing a vertical boundary, we're not seeing a horizontal boundary. So either we have really, really poor fracture conductivity, or we did drill this well into a very complex faulting. And I know we love to blame faults for everything, but it is possible that we went right through a fault system that has, a very, very prolific, unfractured network that we saw early. But anyway, that radial flow period lasted for a little bit of time, about 10 material balance days. And then we popped into a second flow regime that's really interesting. We went right into a transitional flow regime. So we skipped linear flow and went right into transitional. We've been seeing this a lot in the Delaware. And what that is if your fracture network begins to interact with a depleted area. So in this case, I kind of did the classic engineering mistake where I loaded up all the data, saw this, thought, hey, that looks weird. And I looked at a gun barrel and it's like, oh, there's an existing well 300 feet above me. And so I would speculate early on that we hit our boundary out of radial and then went into this transitional flow. And it's in that transitional flow between linear and boundary dominated because we were getting some of that depletion effect. Now, over time, we were able to notice that the well went into a much more traditional linear flow pattern. So I'm going to say whatever that, and I'm speculating that's a vertical related depletion, that there was some sort of equilibrium that hit, then we got a traditional linear flow through our fractures. And then the very last point you can see here, number 4, that's associated with a boundary dominated flow. Now, I want to talk about this boundary dominated flow fit really quickly. It fits perfectly with boundary dominated flow. I don't believe we're actually out of linear flow at all in this well. The reason being is this period started at a material balance time of like 500 days. And this well's only been online for 250 days or so. And there's some literature out there that says you don't really want to call a time to end a linear flow on a time step in material balance days that's way outside of real time. Because what you're probably seeing is your well had some fluctuations somewhere in the process where you had some rate dips, and it flew data points way out there on material balance time and gave a assumed boundary dominated flow. I actually read that out of Dr. Clarkson's textbook, and you were referencing somebody else, so I apologize if somebody else is the progeny of that work. But thank God, I would have called linear flow too early, I think. Anyway, so I'm sorry. Moving into the analytical RTA view, like I said, I think this is still linear flow. You can see the production is kind of fitting that pink line pretty well. But just as a throwaway data point, I went ahead and picked a time to linear flow when I saw my derivative kind of go wild. So the reason why I did that is I just wanted to back out a rough idea of what my fracture half length and permeability is reading if I were to call that end of linear flow and just call it a low end half length. And of course, there's a bunch of assumptions that we can talk about all day about my height and my number of fractures and all the rest of it. But point being is I look at that effective permeability for oil, seems quite low. I know it would get lower if I picked it further out. And I've got a fracture half length of 220 feet. Okay, moving on though, I went ahead and ran a numerical rate transient analysis on this. Now, for those who are not familiar with this methodology, it's a really clever methodology. Kudos to Mr. Bowie and his entire team at Apache who came up with this. But more or less, they model what the predicted flow rate would be if you were in infinite acting flow forever. And then you can make a ratio with the observed flow that you're seeing. And that ratio has incorporated compressibility of the fluid and PVT properties, and more or less pumps out this plot where when this plot is flat, you're still in linear flow. And then once you start feeling boundary dominated effects, it will keel over. So I look at this plot and I feel pretty good about my previous supposition here, which is that we're not out of linear flow yet. Now, that's when everybody goes, well, okay, stop, I guess we're done here. But we still have to plan a development drill. This stuff happens all the time where we're going to do a spacing test. It's been 280 days of production. Nobody's going to hear the reservoir team say, oh no, wait a little longer. So what I'm going to do here is that you can see I picked a linear flow that looked reasonable. So I'm watching this cumulative LFP, and I picked one that I think would be a reasonable place to be once it keels over. And that pumps out some fracture parameters for me. So I can see here I got an effective permeability of 331 or 731 nanodarcy, fracture half length of 384 feet. Okay, now what I do is I take all these parameters, and you can see here my GOR fits pretty good, my water cut looks pretty good. I did a lot of rel perms here, yada, yada, yada. Now we're going to move into a numerical model. So I go ahead and put it into a single well numerical model and just see if I get a reasonably good match. The goal here isn't to get a perfect match on the data. The goal here is to get a representative stream from a well. So, and what I mean by that is you can see here in my bottom hole pressure, I've used Whitson's functionality to just make a smoothed bottom hole pressure line where I tell it where the end of bottom hole pressure should happen. I'm trying to relatively fit the real data, but I'm not super concerned about nailing it, because what I really want to see is an oil rate that makes reasonable sense for a well like this, and a GOR and a water cut that are behaving with the rel perms that I've selected. So this was the model, looks good to me. Then we go into the multi-well numerical model. And this is where we're going to get our first sensitivities on spacing. And so what we do here is we set up a layer cake model, a very simple layer cake model with the petrophysical properties that we have in-house. And we create a parent well where I just put it way the heck out there. I just make a well that's got all of the same properties as the single well that we did here on the outside. And then I create 3 other wells that are all going to be the exact same well, the exact same bottom hole pressure assumptions, the exact same PVT, the exact same rel perms, the exact same everything. And what we do is we just start iteratively spacing these wells closer and closer together. So we're making some pretty big assumptions. We're making the assumption that the conductive height is the same, no matter how close they are, the length. There's a lot of things to hate about this, but it's also a situation where we have to get some kind of sensitivities around the mean here. And so you can see it pumps out all these different oil EURs, and boom, I get what we call the spacing degradation table. So if I look at this from just a straightforward perspective, I'd say, okay, at 6 wells per section, I still wouldn't, on plane, I still wouldn't expect to see any degradation. But then as we space the wells closer and closer together, we're seeing more and more degradation, and I can at least have a point estimate on what my spacing will do. And we like this because it's simple, and we like this because we can also take any depletion effects that are happening around it and also apply it on top of that. So, when we tie it all together, what we really want to do is give everybody a really good idea of not just what we expect to be the outcome, but what are the possible outcomes. So here's an example of a simple Python code that I have where all we do is we have sensitivities around operating expenses that are measured. So, whatever we thought our operating expenses would be and what they came in at the last 18 months to 24 months. Same with CapEx. We have a lot of data on did we hit the CapEx that we thought we would. Oil price, of course, the data on oil price we have for the trailing 24 months. And then performance would be like what's the standard error of your type curve, or what is the inferred error from your volumetric work. And what you can do here is I'm running 4 Monte Carlos in parallel. And each simulation puts a nearly translucent dot for whatever category it's for. And it creates this electron cloud, so to speak, of what is a likely outcome. So you look at operating expenses for this example well, it's highly likely we are plus or minus $300,000 when this is all said and done. And very low likelihood we're outside that mark. CapEx plus or minus $1.5 million. Oil price, you can tell oil price is a little bit stable here for the trailing 24 months. I don't know if I really love that sensitivity, but there it is. And then performance is also the plus or minus 3 million here based on the inferred standard error of our type curve. And what's nice about this plot is there's a lot of accountability there, because 207 days after these wells are producing, I get to then put a dot on where we actually landed, and we can all make fun of whether or not the estimate was right. Okay, we went through a lot there, and I don't think I'd be a good engineer if I wasn't going over the pros and the cons of the methodology I just gave you. The pros are it was very fast. There was physics incorporated in this process. It is very repeatable, and it's pretty robust. Robust meaning I can tailor this to my individual situation. The cons, of course, are that it's very assumption heavy. So if you ask me, where did I get my number of fractures I assumed? Well, I have 5 fiber optic wells we did over 10 years, and that gave me a rough estimate of how many fractures that we have that contribute per stage. where'd you get your height, John? Well, I did some DQI experiments in a landing zone I think is similar, and so that's the height that I'm going to use here. So there's a lot of assumptions you stack on that really definitely make it overly simplistic. If it was up to us, we would do a CMG model or a ResFrac model every time, but our development cycle is just way too fast for that. Those results just don't come out in a time period that's good for what the corporate targets are. And of course, there's the propensity of circular reasoning. I think everyone in here has done this, where I assumed A to calculate B, I used B to calculate C, and then like a week later, you're like, hey, the answer is C, so A is definitely right. There's a lot of unknowns, and we're doing the best we can. And of course, there's digestibility. Like I'm sure, even though all of you do this work every day, I lost you somewhere in this 15-minute tirade. But that is an example of how we would take an appraisal zone, a very complex development, and try to get some reasonable assumptions on what the spacing would look like.
Thanks, John, for the presentation. Yalda Barzin with ExxonMobil. I'm really happy that you have that last slide that shows the pros and cons, and I'm really happier that you mentioned how assumption heavy is our work in general, and it's not you, it's not Devin. This is an RTA heavy workshop or conference, and I guess all of us can talk about the assumptions in Permian. And the topic of this talk is RTA guided development in the Permian. So I thought that maybe I'll just have a couple of questions about how comfortable you feel with those assumptions. Again, you nailed it, but you sound like a very technical person. How comfortable you are knowing that, especially about the height assumptions that I can get into a little bit right now, but how comfortable you are navigating the uncertainty of those assumptions. And I'm just going to add about that height thing. So I don't know if you had time-lapse geochem or not, but we're learning more and more in the Permian that our H is not 200 that you've assumed. It's not even 300 at cases. It's 500, 600, depending on the target zone. And so if you could just elaborate a little bit about the height and your assumption there. And also a question I should have asked before that, are these single targets or it was more of a cube? Because if it's cube, how do you tackle the vertical interference? Thank you.
Yeah, it's a great question. We do use a lot of time-lapse geochem and other diagnostics to try to circle around what we think are good inputs for models such as this. As far as the comfortability, everybody here is working on different basins that have different, what I'd say is a risk tolerance. So my comfort level is high, not because I'm so concerned about nailing these estimates, but it's because traditionally Devon's been very conservative. And so we have a lot of economic room between where some of these wells have been coming in for a few years and then what would be a not break-even cost. So I kind of touched on risk tolerance. And the thing is like I have a lot of risk tolerance for getting aggressive in the third bone lime when I'm drilling 14 Wolfcamp A's below that development. I have so much room there that I'm afforded the opportunity to take heavier risks in that development. Now, if I were to do, say, a simple infill of Wolfcamp B, a zone that we're still characterizing, and it was next to offset Wolfcamp B and then underneath existing Wolfcamp A, now I'm getting to the uncomfortable part where I would likely still do this workflow. But I'm not hanging my hat on that workflow. I'm trying to do recovery factor work that I can, and calling in people from our integrated reservoir team who say we'll use CMG learning so we can get a lot more nuanced. So I hope I didn't give a non-answer there. It's just it really depends on the development, and I do think that. Given our situation where we do have a lot of room from, making money to not making money, and also, frankly, where we are in our life cycle. And what I mean by that is the Permian is a rare thing. It's a special thing. It's quality inventory that gets lower and lower every year. And so we're really much more in inventory management right now than we are in other, I would say, like, targeting a high production number, or, absolutely maximizing NPV every time with no tolerance for failure.
Again, as a Sharon, thanks for the presentation. If I captured correctly, you are trying to use descriptive tool, which is RTA, to inform a prescriptive tool, which is a simulator. I think up to that I was able to follow. My concern there, though, is when you try to use that descriptive tool outside of the range of descriptibility that it has, meaning, so you're putting wells together, but you're not considering fracture interference directly. You're assuming that you're going to be able to frac those wells and create the same length that you are creating in the RTA case. So as soon as you put the wells closer, you're going to have different interactions. So how do you capture that, especially when you start going even deeper there and trying to put capex into the middle of the kind of stuff? So how do you really use this to make decisions, knowing that big constraint that you have?
So if I understand your question correctly, you're asking specifically about the fracture geometries not changing.
Correct.
As we space it, is that right?
Yes.
Okay, so we do have different teams that certainly focus on like gopher modeling for what the effects would be if you get them closer or further away. And then we also have a ResFrac project at any given time occurring in the Delaware Basin. So really, what I have to make sure I do is when I make these models, that I'm talking to all these other teams that are doing this and getting an idea of what a reasonable tuning is. Now, in the perfect world, I do a full ResFrac model for a development every time. But the life cycle of that is months. It's 6 months, 7 months. And I do, not just me, that was really selfish. There's like 4 of us that do 12 of those developments a year. So that's not that level of development that's happening every month. We are planning and then getting approved for the budget for something like that. So by the time ResFrac is done with one section, we've already got 7 on the schedule, and it's funded, and we're running off. So I do my best to make sure I'm speaking with the people who are using much more sophisticated methods on how that looks. In a perfect world, we would do a fully integrated model every time. But it's, that's how we try to do it.
Thank you. Perfect. So now we're going to do a 5-minute break. I'm sorry. I promised 30 minutes, but we have a lot of program to get through, and happy hour that way. So 5 minutes, please get a coffee, go to the restroom, and be back, please. Else I'll call Kumar, and he's going to, whistle at you guys.
No, like I did not feel nervous. I sounded it. Well, you just heard. Let's see. Well, I appreciate it. With that. It's like you can see have more experience in those. Well, I mean, first, no, but that's all for sure. I should be that. I've got 13-year-old. Somebody's talking.
No. We need to get started again. Where's Kumar? I need a whistle. It's pretty good. You do a louder one. I need all the extra juice. I know it's fun to talk together. I promise there'll be a lot of talking. Yeah, that'll be fun, you know? Yeah, exactly. Graham Helfrich, my dear friend, we need to take a seat. This is the best part. Yeah, exactly. Where's Kumar? Okay, we're gonna get started. Probably mute to these people online. Little screen. They were live online as well. And with that, I'll give the slide deck and clicker to you, Jenna.
Okay, thank you so much. Good afternoon. I'm Jenna Anaya with Continental Resources, and I am with the Reservoir Solutions Group. My concentration within that group is data systems and integration. After we bought Whitson last year, I set up our daily data weekly process integration to load all of our wells into each of our basins, and then just recently completed the integration that loads our flowback data. And so I've been in the technology side of the business for about the last 7 years. And so I haven't been doing engineering. And so Matthias thought it would be really funny to punk me and ask me to do this exercise. And I fell for it, hook, line, and sinker. I had some distractions from work, so I didn't really get to finish the exercise like I wanted to. He asked us to do an oil type curve and a gas type curve. So I just did the oil curve. And so here we go. And I'll give you your $20 back after the presentation. Yeah. Okay, so the first thing that I did was I reviewed the data set and just to see what they had sent us and discovered that the data set was configured where all of the reservoir properties were the same. So these are Woodford wells, so I can assume it's the same reservoir. And so that I didn't need to go any further in analyzing that data. So then I started looking at the lateral lengths of the well set that they gave us and determined that out of the 96 wells that were in the data set, 21 of them were in the 9,900 foot range, and the other 75 were in about the 4,800 foot range. So with that, 12 of the 21 longer laterals had reported values of proppant and fluid, and the others were blank. And so I assume that the completion metrics of the ones that were not reported were within the average. And so and part of the exercise was to do a 10,000 foot lateral with 2,500 pounds per foot and 60 barrels per foot. So the proppant averaged 2,450, and then fluid averaged 57. 4 of the 12 wells had over 3,200 pounds per foot of proppant used, and 4 had less than 2,000. So 69 of the 79 shorter laterals had reported values of proppant and fluid. Proppant averaged about 2,600 and fluid averaged about 60. So the next thing I did was I added a manual DCA forecast for all of these wells. I had done an auto forecast, and for some reason I'm not sure that I did that right. And mind you, I've never used the top curve module in Whitson at all. I mean, one of the reasons why he asked me to do this is so it could kind of showcase the intuitiveness of the software, and that somebody that doesn't really use it or do this type of work every day can pick it up and do something with it. So I did manual forecasts. I'd used the auto forecast. Don't know what I did wrong. Those EURs came out to 0. So I quickly declined all of those. Well, I'm sure it was me. Don't worry. So I quickly analyzed those. 84 of the wells had production, and then the other 12 didn't. So the methodology I used the auto fit and rate versus time, and I did some minor adjustments really quickly if the cum versus time looked unreasonable. So ways I used to scale this, because we had a lot of the wells had the shorter laterals, normalize the production data, barrels per foot of lateral. So the metrics from this conversion gave me a little insight into how the wells would scale. So the metric for the barrels per foot EUR is roughly double from my results, scaling from 5,000 to 10,000, but the metric for actual production is close, and then as well as the BOE per foot metric. So the metric for the 10,000 foot wells came out, almost double what the 5,000 foot laterals were. That doesn't make sense to me. So you would think that you would have degradation as you get a longer lateral in your barrels per foot, and it probably shouldn't double. So I didn't really trust that number, which means there was something in my EUR forecast. The actual production came out really close, and the other one was fine. So the one thing that I might change if I were to go through the exercise again is look at the metric for the actual production on a more normalized basis, like a 12-month, first 12-month period. Okay, and so then the other thing I did was I adjusted for spacing. So if I had any unbounded wells, I took those out of the well set. Okay, so this is the well set that they sent us initially with all the 96 wells, and so that's what the picture of my data set looked like once I got rid of all of those individual wells that were not bounded, and so I got a little better picture. I might have done a little better job, going through this to eliminate some more, but that's what I decided to go with. Okay, so I reviewed my DCA forecast, and it looked like it would have been underestimated as evidenced by the P50 comparison. So I said, you know what? Now I'm going to go and I'm going to look at forecasting on my averages. Okay, so looking at that, that looks pretty good. I came out with some numbers for arithmetic mean, geo mean, P10, P50, P90, and I looked at my P10 over P90 ratio, 3.7. That was within an expected range there. So I like the way those curves look. And so here are my results. My geometric mean was 245, arithmetic mean 260, P50 263. And so that lines up with my expectations. I think those numbers look reasonable based on the data set that I worked with. Okay, so that's all I got to. I did not get to do the gas curve, and so I'm not going to let y'all answer questions because we need to get to the next presentations. But so I'm going to do a Q&A with myself. What's your favorite software? Of course, it's Whitson. And then on a scale of 1 to 10, how would you rate it? Well, it's an 11. So really appreciate it. Thank you very much.
And that's also another part of doing whitCon. And we try to like lower the bar. And it's very sporty of Jenna, who, you know, it wouldn't be a natural part of her day-to-day job to do this. And you killed it. So that was awesome. The difference with her numbers and the others is that she followed 10,000 feet, while Alex and Jason will show results for a 3 miles. So with that, Alex has just joined Murphy, and he'll take us through the next few slides.
Okay. All right. Yeah, my name is Alex Galley. I'm a reservoir engineer in the Eagle Ford team at Murphy. I've been there for a month, and then when I joined, Matthias asked me to do the presentation here today. I'll try to blow through the slides a little bit quickly, as it's 10 minutes. But anyway, just to recap, he provided some data in Whitson, and full disclosure, it's the first time I've actually used Whitson. I've used similar software before. So, I used it in conjunction with Spotfire. Maybe some of the things in Spotfire could be done more efficiently in Whitson, so I apologize in advance. But I just kind of used the process that was familiar to me. But as a preview, what I found Whitson was really useful in for type well development is automatically forecasting a number of analog data sets or PDP wells very quickly. I went through them. I didn't modify them manually, and then obviously developing the type well. But anyway, he provided a number of analogs to the west of a proposed DSU. All of the analogs are kind of 5,000 footers, 10,000 footers, and he wanted to come up with a 15,000 foot. So this is just an overview of the process that I normally use. But, the first question to ask is, what is this for? If I'm at a bank on the sales process, I probably want to be a little more optimistic in the type curves. As far as the performance is concerned, spacing and the CapEx, I kind of approached it as if I'm doing an AFE. So trying to match the average more or less, as long as there's no any outliers, or once I remove the outliers. And then if I'm doing this for reserves purposes, maybe I'll try to match the P50, kind of be more conservative, or even a little bit more conservative than that. So the process for me is iterative as far as exploring the data, developing type curves, then looking at the results, maybe coming back, revisiting some of the assumptions, changing them, coming up with the new type curve development. So again, it's not just a path from A to Z. Sometimes it's kind of a little more iterative than that. Again, for the purposes of this evaluation, I just kind of said I'm going to approach it like it's an AFE. As long as there's enough analog data sets, I'll try to come up with a type curve that matches the average performance more so than the P50, let's say. So as Jenna mentioned, I also kind of reviewed the data, wanted to make sure that it was just all in one interval. As you can see here, all wells were in the Woodford, all horizontals across 5 different companies. Wanted to kind of understand, okay, what has the evolution of the pounds per foot of proppant been over the years? Looks like, with the exception of maybe of a handful of wells, everything's right around 2,000 or greater pounds per foot of proppant. The fluid, is pretty aggressive too. And then the lateral lengths, you do see an abrupt change in 2017 to 2019, where generally they became, they went from 5,000 to 10,000 footers. Also notice that in the Whitson data, the proppant intensity information is missing after 2017, but maybe that's just the way I exported the data from the Wellmaster in Whitson. Murphy does have access to Enverus, so I kind of pulled the data in Enverus. Typically, depending on the type curve evaluation, especially if it's a big enough AFE, let's say, whether operated or non-op, but sizable investment, I'd like to chat with a geologist just to make sure that he or she gets a chance to review and say, when we're picking our analogs, I want to make sure that geologically they're in a similar rock quality area. Maybe a proxy for that could be TVD, reservoir thickness, or what have you. Also, just bringing in geologic layers. Here, I didn't have a geologist, so just looking at Enverus, you can kind of see the blue lines there. That's the delineation of Enverus type curve areas. A lot of times, that's because rock quality could be different across that boundary. So, looking at this data set, I'm probably not going to include the wells to the west of that boundary in my type curve evaluation. At that point, I brought the data into Spotfire, again, from Enverus and from Whitson, just to kind of understand, okay, what's the well spacing like, and the data set looks like. I didn't want to make the slide too busy, but generally, most of the wells here were about 500-foot well-to-well spacing. And then the yellow wells are kind of Devon. They had quite a bit of development. Most of theirs were about 500-foot spacing, although the longer laterals to the southwest looks like they drilled about 4 wells per DSU. Longer laterals, it's maybe about 1,000 feet well-to-well spacing. So it does look like maybe the trend is to upspace, something to keep in mind. Cimarex in the very west of here in the blues did go down to about 200-foot well-to-well spacing, but since then have upspaced. Normally, depending on the area, I take both the lateral lengths and well spacing into account when scaling the wells when coming up with type curves. In this case, I didn't take spacing into account. I just filtered out the wells that I deemed to be spaced too tightly. And again, I'm not going to belabor every single slide here, but one of the things I like to do is just identify outliers that don't necessarily fit the data. So here we have one well that drastically outperformed everything else, and then some wells at the bottom that drastically underperformed. So just went ahead and removed them. Again, over the next few slides, you kind of see various diagnostics that I like to use to kind of understand the data a little bit better. The map on the left is color-coded by operator, and then the size of the bubbles is by EUR per foot. So it was kind of cool. Yeah, in Whitson, I just very quickly came up with EURs for each of the wells. And then when I reviewed them individually, I didn't have to manually adjust them. I felt like the fit was pretty good. But you know, here on the left, just looking at the comparison of spacing to EUR performance, it does look like generally nothing jumps out at me. The wells with greater spacing seem to perform better on an EUR per foot basis. Generally, I use BOE 20-to-1 ratio. And then on the right, again, just similarly, the bubbles are EUR per foot, and then I'm color coding it by GOR. So just kind of seeing aerially, is there anything that happens to GOR? If you ignore the Cimarex wells that are super tightly spaced, as you would expect, the GOR is higher there, it's more red. But generally, ignoring those wells, as you go west, it looks like the GOR increases. But again, I'm probably going to exclude those wells from my type curve development. Closer to the type curve area, I do notice there's a couple wells that have very high GOR, and something seemed to be wrong with their performance. I ended up excluding them. Normally, if something like that were to happen, especially wells that close to the DSU, I'd want to figure out what happened. You know, were they just landed not in the right interval, maybe the artificial lift design, or whatever else, something impacted their performance. And if I can't explain it, I'll probably end up risking the type curve forecast accordingly. Here I've got spacing on the x-axis and BOE per foot on the y-axis. So just kind of noticing a trend, as you'd expect. As you upspace, the BOE per foot increases, but above 600 to 800 feet, it seems like it flatlines, although you don't necessarily have a lot of data beyond 800 foot of spacing. But again, my recommendation here would be probably keeping it at 600 to 800 feet of well-to-well spacing or above, based on that plot. Now I've got completion date or vintage on the x-axis and BOE per foot on the y-axis. It does look like generally you're not seeing big changes in performance. You do notice the color coding is the completion intensity. Green is higher, red is lower. Seems like there's some correlation with BOE per foot there. Then I looked at GOR color coding, still proppant intensity color coding, spacing on the x-axis and GOR on the y-axis. It does look like on the left here, anything 200 feet or less, as you'd expect, the GOR would be higher. Then that's in fact the case. So again, based on this plot, I wouldn't recommend spacing it tighter than 400 feet, just because the GOR blows up. So that's an indication of you're just too tightly spaced. There's well interference. Here I've got spacing on the x-axis, proppant pounds per foot on the y-axis and color coded by BOE. Again, you expect the bigger the spacing, the larger the proppant intensity, the better your EUR per foot. I'm not necessarily seeing like a huge correlation here, but somewhat of a correlation. So at this point, I'm getting ready to develop the type curves. Just to recap, we reviewed the spatial well performance and identified analogs with similar pounds per foot and spacing as the new drills. One concern I've got is there's two laterals with very high GOR located very close to the DSU. And then also most analog wells are 5,000 footers. So there's a handful of 10,000 footers. And we're planning to drill a 15,000 footer. How do you want to handle the scaling? We don't necessarily have actual data to figure that out. What we've done in the past in similar situations is maybe for the initial 10,000 feet, you kind of give it 100% of the scaling. And then for the incremental 5,000 feet, maybe risk it down by 20%. But in this case, I just scaled it linearly, but that's something to keep in mind. And then obviously, the inputs from geology would be useful here as well, just to understand if there's geologic faults that maybe drove performance of the analogs or of the new drills in the DSU. Again, in the absence of geology, interest of time, I just kind of pulled wells in from within a 1 mile radius of the DSU. You do notice here that there's lack of data to the north, east, and south. Most of the development is to the west, so you kind of wonder, is this kind of a step out? That's an additional risk you got to keep in mind. And then I went ahead and auto forecast all the analog wells. Like I said, I was pretty impressed with this, very quick. And when I manually reviewed them, I agreed with all the forecasts. So I'm not going to go through each one here. But one of the QCs I like to do is just put them all in aggregate, and the fit looks pretty good to me. And then finally, the type curves that I came up with for oil and gas, scaling it to 15,000 feet. Here, I didn't have to manually adjust the fit, unlike the PDP forecast. And again, for an AFE, as long as there's a sufficiently large data set, I like to use the fit to the average, not the P50. Then more on the cum basis rather than rate time. So I like to fit here for oil, and the same thing for gas. And then kind of doing the last QC, plotting everything against the analogs, and then the statistical distribution. So the red line is my fit. The black thick line is right on top of it. That's the average. That's what I wanted to fit. And then the dashed line is the P50, similarly for gas. So I think it's good enough for this evaluation. So that's it for me. Okay.
It's excellent. And one of my shtick is software is not a substitute for thinking, and you can see clearly that both Jenna and Alex here has done a lot of thinking. So there's a lot of process going in here that I think people can learn by osmosis, or bring into their own workflows as well. The last person to present on this session is my good friend Jason. He has lived in Norway, so he has developed this love for Norwegian chocolate. Talk to him about that in the break. World's best chocolate. I don't know if he's going to share any, but we'll see. Okay, there we go.
You're good. All right. Yeah, Jason Billings with Civitas. I've been there about a year. And yeah, here's my look at these wells. So looking at the data, it looked like it was based on the GOR, this was a condensate gas play. No water production data given. I assume it's not required in Oklahoma, but I don't really know because I've never worked Oklahoma. Glad we all came up with the same 96 well data set. A few were duplicates, and some were missing production data, but I added it back in. So I ended up with 91 wells to forecast. I did use auto forecast just with the default values because, again, I didn't really have any preconceived notions of what they may be to generate the 50-year oil and gas EURs. And then QC'd those forecasts kind of manually adjusted as needed. Let's see, we got the pointer. Which one's the pointer, Matthias? Let's see, this one. And again, sorry for the ladies and guys over there. So a couple of those adjustments here. This is an oil forecast. The auto fit is in black. My forecast that I adjusted to is in purple. And I guess I'm just not in the camp of the more dots you fit with your line, the better the forecast. So what I did is kind of forecasted later out in time. And the thinking here is that, early in time, you're having pretty massive changes in drawdown. And then hopefully that's, less more stable here out in time, and also hopefully you're on your kind of final artificial lift setup. So anyway, the other one here, a few of the wells had these sort of jumps, some kind of change in drawdown. And again, the black one is the auto forecast and kind of missed this last jump, so I just put it through there. So, if we probably need to have something in there that kind of we can, bias to the last year, the last 6 months, and maybe that's already in there. Where did Matthias go? But if it's not, let's put it on the list where you can, wait the forecast to the last bit, just to get that right in case of situations like that. So the analog data set. So again, we're given kind of the problem statement. As being the third one, you get to hear it a couple of times here. But anyway, it was a 3-mile well with 2,500 pounds, 60 barrels a foot. That's where you need to go. So I looked at wells. I kind of reduced it down to 49 barrels for wells that had 49 barrels to 70 barrels a foot for the completion for the fluid intensity, and proppant intensity needed to be over 1,900 pounds per foot. And that got me from the 91 wells with forecast down to 65. And then also in the in the problem statement, it said, spacing should be similar to other wells in the data set. I'm pretty sure some economics probably should be involved in that as well, but it's outside the scope of this analysis. So I selected about 9 wells per section, and that reduced my analog well set from 65 to 38. And that was a map of the two, where I started and where I ended up. So these are the EUR distributions for those different well sets. The gas EURs on the left and oil EURs on the right. Just kind of looking through. So this is all the EUR, so the 91 wells. And as I think this trend is fairly reasonable in what I expect. As you knock out the smaller completions, your EUR goes up across the board. The whole curve shifted to the right. And then as I knocked out the kind of probably mostly tightly spaced wells, but there was obviously some unbounded ones in there. But overall, the spacing call also increased the EURs on the gas. On the oil, is a little more interesting. The P50 really didn't change across these different calls. And was even more interesting, and I didn't dig into it, but the P10 to P90 ratio, 9, 7, and then 2.9. So don't know quite what was going on. Probably had more time, I'd dig into that. But anyway, I was much happier with 3 instead of 7 as far as P10 P90 ratios. Okay, so I did do an independent forecast for oil and gas. But I do believe the more technical, correct way is to forecast your primary fluid and then use a ratio forecast for your secondary fluid. Fortunately, that was still sort of in beta when I was doing this work, but I also have a surprise slide from Matthias at the end, and it'll have a little video of that got released earlier this week to some of us, some companies, including mine. Anyway, so independent forecasts for oil and gas. And then you might have noticed in my analog set that they were all 1-mile wells, what I ended up with when I went down to the 38. I did check that at kind of 6 months. I kind of looked at 6 months for the 2-mile wells that were in the data set, and just kind of, eyeballed that, I'm getting about 2 times the increase when I went from the 2-mile wells to the 1-mile wells if they had similar completion sizes. And so I just, for this 10,000 foot type well, which is what Matthias asked for first, so I just did both. So anyway, that way he can't trick me. And so I basically, fit the data. Again, I also went through the trouble of getting the ramp to a peak rate, but again, just adjusted everything up basically by 2 to fit, although all my analogs are 1 miles, but these are all adjusted linear up to 2, and then fit the EURs to this is the P50 data here in the black, fit to that, and then tuned it into the EURs on the P50 EURs on the previous slide, from those distributions. Same thing with the gas, or same thing with the oil. And then here's my 15,000 foot, the 3-mile. So no 3-mile wells in the data set. So I'm going to assume this is the operator's first 3-mile well in the area. And so I did do a direct EUR uplift, similar to Alex. So I know fill you on, are the toe stages getting the same, quality completion as the heel stages and other issues, but kind of A, there's a lot of uncertainty in the 50-year forecast, and B, that these numbers here are still within the distribution of the 2 mile. If I went back 2 slides, you'd see they still fall on the upper end of a 2 mile distribution. So it felt okay about lifting those all the way up with no kind of degradation, but somebody can let me know in 50 years if that was a bad call. But on the peak rate, which you will see in my lifetime, I did just give it a 25% peak uplift rate. And that's because a lot of times when you go from 2 to 3 miles, the operator won't change the tubing, won't change any of the surface facility design, and maybe not even change the choke schedule. And so you may not get the drawdown, the same type of drawdown on the 3 mile well that you did on a 2 mile well. So anyway, my type curves wrist a bit on that. So, and I got Matthias's slide that shows the new ratio forecasting stuff that was put in earlier this week. And that's really all I know outside of it. Probably runs for a minute, so I'll stand here awkwardly. Is there anything else, Matthias, I should say about it? It looks cool. I can't wait to give it a try. It looks pretty fancy. Good job, I guess, to the Whitson team. I know there's multiple guys and girls working on this stuff. So, but yeah, that looks fancy, no doubt. I know it was a pretty long video. I was like, it's a minute long, so I can only stall for so long.
Give Jason an applause. And what we're showing here is that not only, even when you do it on the primary phase, you can do that, but also here is like the power law, GOR type of recommendation from Fulford. We've implemented that as well. So you can do the power law fit on the ratio, and then you basically get the DCA forecast. So that's a thing we're really excited to have worked with Fulford on as well. Perfect. We're going to change gears. So it's a little bit lighter now, since at the end of the session or end of the day, we are going to stay on this kind of like one data set, 3 interpreters. Again, I need to remind the presenters, and that's my fault, just to try to stay to between 8 to 10 minutes. And Liz is like, oh, you said 30 minutes for me, right? Yeah. Yeah. Well, I also added an extra well after I got them to commit, but that should be good. It was a gas well, so it should be a fairly straightforward one. We're gonna go smack. It's gonna be Liz from Marathon, and then Joe from Ascent, and then Avery from Silver Bow, Javelin, Crescent Energy. There's so many names for you guys now, so I'm gonna do that. So we're gonna start with Liz, and she has a bunch of jokes as well. So I was like cracking up when I read them yesterday.
I'll try to speed it up a bit. But Liz Brescher from Marathon Oil. I guess originally I'm a chemical engineer. Started in chemicals, went to refining, and now I'm in reservoir. Fairly new to the RTA, so we'll see how it goes. Multi-phase RTA, these are the steps that I have gone through to do this analysis. Ready to analyze, really tricky assessment, really tired analyst, ridiculously tough analyst, and now real-time awkwardness. Oh, sorry. Yeah, awkwardness. I'll stop looking up there even though it looks bigger and prettier. So here's the assignment that Matthias gave us. Everything is about the thought process, so just keep that in mind. Estimating LFP, your contacted in place, and your EURs. Along the way, I use a lot of lifelines. These are on the right. And since it's after lunch, and lunch was totally bussin', I'm hoping most of you are falling asleep right now. And if not, you're going to join me on this journey to hang with a 6th grader. So my daughter is in 6th grade, and she's been teaching me all this Gen Alpha style lingo. So hang with the cool kids. So here's the task at hand. I'm going to go ahead and skip this. I was really just poking fun at Matthias and all the tidbits of information he leaves out on things and stuff he likes to do. But really the first thing is scour the data to see what was given. I really thought he was Delulu. I mean, this well was totally sus. When I loaded everything into the software, I'm ready to go. But what's the first thing you're supposed to do as an engineer? QC the data, right? Well, I QC the data in the software. I did not go back and look and see that the Excel did not load properly into it. So I did this whole analysis, prettied up my slides, was ready to go, feeling good. Yeah, we missed that. So ensure that data from Excel loader is properly populated. You don't want to be phantom taxed. So you don't want to be missing some of your data. I asked the host. So this is my first lifeline. I called Matthias and was like, what the heck did you do to me? And then I calmed down. I was like, all right, I got this. So just in quick looks of the data that I did review, overpressure gas well, dry gas with no condensate. Those are probably the big things. The one thing I did do that was a little different, the data set had 9,800. I could not change it because the perfs were showing that was 9,268. So that just, I couldn't do it. And then anybody throwing darts later on, this is looking like a Haynesville well to me. So dry gas well, PVT, pretty easy, right? Dry gas method, 0.55 specific gravity. Matthias also told me after I was done, 0.6, but we're gonna roll with it. Quick look at the DCA. I didn't spend much time on here. Looking at your rate cum plots. Did that, you do notice that the pressure is stabilized, but it's at about 4,000 or 5,000 pounds. So not quite going to be an apples to apples comparison at the end when we compare it to numerical model. But 26 Bs, what I got. I did QC that kind of about, hey, what does it look like after a year, 2 years? On the bottom hole pressures here, they gave us 10,000 pounds. Just looking at it, use the gray correlation as gas. And then looking at the first hydrocarbon rate is pretty close. And then I did try their IPR analysis. Gave me about the same this time. So I just kept with the 10,000. Everything looked good. Flexing my mad skills here. FMB, matched that shallow slope. Here it was on the later half of the well. The pressure was above the bottom hole pressure here, but we didn't have any like shut-ins to really compare to. So my contact is in place. As you'll see when I went back and circled back, it is a little bit low on here, but I will circle back to that. That's a facts. On the ARTA, this is not my specialty, so I was going to call in the 2 other presenters here and kind of learn from them. But I did a gamma 3.25 to start with, just kind of based off of experience that we've had with some really high pressure wells, not necessarily in the Haynesville, but just general experience. Ran with that. We were getting about 0.5 on the fractional RTA for the delta, so not too bad. But when I went to do the classical, I was like, what the sigma? Feeling major cringe here. I was getting a really high OGIP. So maybe pressure with the overpressure issue with the gas. I'm not quite sure here. Like I said, I'll check with the next 2 in a few minutes. Tried it again, trying to double dip here. I couldn't really get it. Got it down a little bit by messing with the gammas, but I didn't like the match. So again, I'm passing on this one. The numerical RTA here, we seeded it with that FMB to start. I locked it, tuned the water, set matrix and fracture rel perms to match. I did have to drop that conate water to get it because the water saturation is pretty low here, just to get some water to flow, decrease the KRGRO. Then adjusted the LFP line and I got my results. Big W here. Faith has finally been restored. OGIP 47, LFP looked good. Circled it back, and if I increase the pressure a little bit on that FMB plot, I can get it to match. I just don't have a basis for that without a shut-in. History matched, and then forecasted through here. I ran it on gas control, then I flipped it to bottom hole, make sure it didn't look too erratic, as a few people in this room have taught me. Set my limits, and we got about 47 Bs, EUR 39. So Gucci when it works. As Matthias said, it's the result. It's not about the results, it's about the workflow, but here's what we got. So that analytical definitely had some trouble, but everything else seemed pretty reasonable. Moving on to the gas, this is where I'm going to phone a friend or ask the audience, because in my quick looks, there's something funky going on at the production data. Around 150 days, we're starting to fall below the saturation pressure, but we're also just had a shut-in. They started injecting gas at the same time. And I'm not really seeing any of those rates change like I would have expected. So something's going on here. Is it liquid loading? I'm not sure. But what I will say is in the data that Matthias stripped from us, you can start seeing in the future that they did add a rod pump in about 6 months, which I think was probably a good idea. This one is slightly overpressured, it's about 0.6. He did bias it and tell us that we needed some gamma and we needed to justify it. So I was looking for it, but otherwise I would not have intuitively started looking at a 0.6. GRR, everything here is pretty good on PVT. DCA, same thing as before, nothing too important here. 333. Bottom hole pressures, again, same thing here. I did go ahead and increase that pressure a little bit, given was like 5150 or something like that. When you went and looked at first hydrocarbon, it was like 5367. When I looked at the IPR and everything, I was getting about 5400. So I did go ahead and bump that up and actually help with my matches too. Contacted plates, here we did have that build up. So I did move that up. I got 2300 in place. On the analytical here, again, nonlinear fractions got that 0.35. got my LFP. Contact was a little bit lower at the 1800. So don't be so low vibrational about this, and RTA may help. So here I'm going to ask the experts because I seeded with my FMB and locked it. I tuned the GOR in the water, again, setting the matrix equal to the fractures for rel perm. I increased that NG to suppress that GOR, decreasing the KRO-CW and the KRO-GRO. Reduced FCD. It's getting a match in the beginning time, but it's really struggling in that late time. Again, I think it comes back to that production that we were seeing on that graph. But me being me, I had to keep tinkering. So I'm like, well, that match wasn't bad, but it's not great either. It's just kind of mid, feeling a little salty. So I kept trying. Then I asked the experts and they told me, Liz, leave it go. So we left it go. All right. So then we went to the history match and did that. Everything looked pretty good. Got 406 the first time. That's with all the parameters that Matthias gave us. But since the DCA had a little bit different abandonment pressure and things like that, I went and ran it there just to see what I would get, and I got 368. That's all I got. So just some learnings. It's hard to ghost Matthias, but this experience was a sleeper hit. Check the raw data before starting to ensure that the data matches. This made me really ick. Ask my team. I complained no less than about 3 hours. The supported 2 minutes or less is not cap. It's literally seconds, and you better be ready because they're calling you whether you're ready for it or not. I was low-key nervous about this presentation, if you can't tell by my shaky voice, but it was a lot of fun. Its presentation was so lit. I hope you enjoyed it. I have the most supporting and amazing squad. Man, without the people in this room and my teammates, would never have done this. So thanks for the push and the support. And I'm such a stan of these conferences and workshops. Great group of folks learning from each other. And now that I've spilled the tea, I will not share my poem because we're running out of time, but maybe for another day.
That is awesome. I'm actually going to summarize all the different RTA results in there because there's a lot of different things, but I'll try to summarize it in a nice table. We're very sporty, Liz. Thank you for doing that, and apologize for that. That was my fault, actually. It was terrible, absolutely terrible. We're going to go over to Joe from Ascent. He has looked at the same data set, and here is your presentation, and here is your clicker.
Thank you. Hello, everyone. I'm Joseph Kringer, reservoir engineer at Ascent Resources. So we're up in the Utica looking mostly at dry gas wells, and that's kind of my perspective that I bring into this. So we'll obviously start with the dry gas well too. And so I had the same problem whenever we loaded it in, but I actually caught that data, but I saw something that Liz caught later that I didn't. So definitely check the data first, but preliminarily, just looking at the wells really quick, I also noticed that we have a really high pressure, high temperature dry gas well, and so also thought Haynesville is probably appropriate choice or estimate here. And so big rate, 45 million a day, held flat for 4 to 5 months. And I also, for people that again, working the Utica, we're familiar with curtailed high gas rates. And one thing I noticed was that the pressure drawdown kind of slams right into line pressure right here. And that was before I checked what line pressure was. And I noticed there's no indication of frictional effects that you'd usually see flowing up casing at 45 to 50 million a day. But then I checked and line pressure is 4,000 pounds. And so that definitely, you're going to mitigate a lot of frictional impact there. So unusual well for sure. And then whenever I saw, we completed the well with over 4,000 pounds per foot and 65 barrels a foot. So huge stimulation. Also, assuming Haynesville, I was thinking higher gamma estimate, and also Matthias told us high gamma on this well. Problem was I was having a lot of trouble getting a good gamma match, or at least a data trend that I was familiar with and trusted. A lot of the times whenever I threw the gamma up into the 4, 6, or 8 range, I'd get some odd trends in my data that I didn't really know how to interpret. And I think there might be ways to interpret it better. So I kind of retreated back to my comfort zone, set the gamma factor at 2, and proceeded. I do think if you had analog wells with shut-in like this, you can tune your gamma factor a lot easier. I also thought it'd be nice if I had more time, maybe fiddle with that fracture gamma, especially thinking about the size of fracture that was put on this. Because I was getting, with high gammas, I was getting huge XFs that I didn't know if I could really justify. With that, going to DCA, I just am used to forecasting wells off of a rate time plot, and so that's what I did, but I threw a couple different B factors on there trying to get a range of what an expected EUR would be. One thing to think about is if you've got a well that is curtailed for significant amounts of time up front, how should that impact your B factor that you use? And so, this would be an example of that, but somewhere between 1.2 and 0.9 would give me an EUR range of 27 to 34 BCF or 2.7 to 3.5 BCF per 1,000 foot. And so this is a huge gas well. That would be a red flag in itself. Typically, if I was thinking I'd have to go, say I got a 3.5 BCF per 1,000 foot well, but huge pressure and stimulation here. So I'm going to proceed with those numbers and not get too worried. Bottom hole correlation is pretty easy here too. They all lie on top of one another. And with dry gas, I used Gray's correlation. And I don't know if this is technically valid, but I always like whenever my analytical RTA rate normalized pressure plot flows through the origin. And so if you're fiddling with your initial pressure, it makes you feel good whenever that's going through the origin. Going to the FMB here. I was looking for the shallowest slope I could. We had low water saturations here, no shut-ins, and so you really didn't have much to guide your F&B pick, so I just chose the shallowest trend I could find. So the analytical RTA on this one is the one that probably gave me the most fits, trying to get everything in tune with one another. I was getting huge LFPs on the analytical RTA and having trouble matching that on the numerical. I guess that's not that big of a deal on a dry gas well that has low water saturations, but getting LFPs just under 1 million here, contacted OGIP of 50 Bs, XFs of 700 feet, and some relatively tight 80 nanodarcy rock. So, but those were reasonable enough, especially after comparing them to my high gamma picks. So did the same thing in the numerical RTA. Tried a lot of different things and even thought about boosting my kind of LFP line up. So then I always had an LFP above my analytical one, but I forced this to choose 44 BCF for my contacted OGIP from my FMB analysis there. And these are the resulting outputs. XF is 600 feet, perm of 114. Seems to pass the smell test, I guess, to me. So went with that. Obviously worked a little bit on my water saturations and rel perms to get the late water trends there. And so the end result being 30 BCF well, recovery factor of about 68% here. And so here's this little summary comparing all of the different modules. Pretty good agreement here, no problems. Liked that, but then again, the gamma factor was something that is a little confounding. It would be nice to work on that, and I think also the fracture gamma would be great. Okay, keeping pace, I'll go forward into the oil well. So similar ideas here that Liz had. Matthias did tell us high gamma factor here, and so I was like, I'm going to go set it pretty high, be pretty aggressive, and I threw a 6 out there, and I was actually getting trends that were interpretable, so I went with it. The rhyme and reason's not very strong, but we're looking at black oil well with a really stable GOR. This is where I misread it, and I thought we had a rod pump installation here, but I guess Liz said that's later on. But another large completion, moderate pressure, and then just went with the high gamma pick here as well. Very similar trend on the DCA, just used a B factor of 1 and then kind of a low side of 0.7. So I'm looking, it's a pretty wide range, somewhere around 326 to 415 thousand barrels or 45 to 55-ish barrel per foot EUR, so pretty good little oil well. I don't think this is true now. My initial reservoir pick of 5,650 again comes from my analytical RTA, trying to force that data through the origin. It also helped me feel more comfortable with some of my picks later. So you do see it above kind of any of the calculated bottom hole flowing pressures. In our basin, we always use gray. We have some pressure gauges that help validate gray even in our oily side. So I figured this would be a good chance for me to use the Voltas mat. So I chose that. Okay, this is an example. One of the big problems on the FMB here was I was getting some odd water saturations. I think Mo covered this well in the last knowledge sharing event. And so I dropped my water from this FMB plot, chose the flattest line I could, and didn't have any problems with the any really buildups. I was still above most data pressure points, but it gave me a pretty low contacted oil in place. And so I took that with a grain of salt. Lots of this stuff has a grain of salt now going forward. So you've got analytical RTA, some deviation on your rate normalized pressure plot as you come into your saturation pressure. And so another thing where I move forward knowing that I got to take this with a grain of salt. And finally, the module that I think I probably trust the best for this well is my numerical RTA. And so this is giving me an LFP of 366,000, contacted OGIP of 2 million barrels, and XFs 475 foot and 80 nanodarcies. It's tough to validate because the other ones I think are semi-compromised, and so I kind of looked at the outputs here on my numerical model, and it's actually giving me oil EURs of 430,000 barrels, which is even beyond what my DCA is. And so this is one of the few times you get to go probably back to the management and say, hey, we're going to crank our DCA upwards instead of downwards based on the model. And so that's really I thought the trick to the oil wells is just, having to throw out some maybe data that you don't trust as much and just go with the module you like the best. Okay, that's it. Thank y'all.
Yeah, what was very sporty with you, Joe, is you try to pronounce Walsmart and Gayar, and I think only one person I know how to pronounce that correctly, and that's Yalda. And you can ask her how she would pronounce it in the break or the happy hour. Avery's the last one out, same data set, and then I'm going to go through a quick summary presentation before Dave is going to jump us or join us here on stage. So with that, I'm going to give the word to you.
Sounds good. With the given identity crisis that Matthias was saying, I kept it super generic. And a plug for Whitson. Every time I try in the last 2 years to bring Whitson to the company I've been at, I get bought out. So just FYI, if you need Whitson, let me know. But no, my name's David Davis. I'm a reservoir engineer currently at Crescent Energy. And I should have said no. There's been a lot going on, but it's hard to say no to Matthias. So when he asked to do one well, I said yes. He gave me 2. And then I was able to cram it in on a Monday night of this week. So this is the first time I've done an RTA workflow in Whitson, a little transparency, and I haven't touched RTA in like 2 years. So it's always fun to give my first analysis in a while in front of all my friends. So here we go. I'm going to start just from the summary at the end. And so honestly, I could talk from this one page and save you guys a bunch of time. But yeah, work through DCA. So I like to do a lot of ranges. For the sake of time, I just picked kind of a B factor of 1 on the DCA, as you guys can see that fit. And then looked at gas FMB just for fun. I know in the software, really the multi-phase is more than sufficient, and I got some more answers. Then went into analytical RTA, followed by the numerical, and definitely out of practice the numerical, so these are not my best. History matches, it was getting late and I was getting tired, and so they were kind of good enough, and I went from there. So it looks like I was probably optimistic on my LFPs, but definitely was running into kind of a similar situation where I was getting much higher results in my analytical versus when I was starting to get the numericals, and then more or less was kind of in lines with some of the results that the other interpreters had when it came to the EUR. So there's room for interpretation for sure, and that's where we'll go. And then I went ahead and, as I was looking for it, kept my gammas kind of in that 3 range. And then I didn't play with all the well perms, and so I didn't have a great match on water. Honestly, I didn't even show it for this gas well, but it showed the shape, but it was low, so I knew I needed to just tweak it, and I didn't get to that. And then there were definitely some questions on the well history. So in a similar thing, definitely saw, I do work dry gas to volatile oil windows, so I've kind of seen a few. You told us this was Eagle Ford. This didn't look like an Eagle Ford well, so it makes me feel better that it likely wasn't, because I don't see these kind of rates in any of my wells. But fortunately, I did a perf check and caught that the lateral was not what was given to us, and so always good to QC your data. I didn't have a gamma, but I just looked at some PVT wells that I had, and it's usually 0.6-ish, 0.59, so roll with that, and I guessed correctly. And then I was using their IPR analysis, and just to kind of validate, we had given
a 10K PSI for a start, and it fit pretty well. I was just checking. Matthias will trick you sometimes, so I was just making sure the data was good. So that was kind of the setup on that front. And then getting into the fit, I mean, obviously the flat period, and so without any sort of pressure normalization, so it's hard to see, but you did start seeing a decline. I just rolled with the 1. A lot of times, kind of like previously, I like to do a range of B factors since looking at that acceleration term changing, it gives you different results. And then jumping in, looking for that slope, checking against your average pressure to measured, was getting kind of in that 40 BCF range. Jumping then into the multi-phase, I clicked on and off water. It's a low water producer, so it didn't change the answer, but I just wanted to kind of double check that from a tank size, there wasn't big variations. And then jumping into the analytical, it's single phase, so that worked out well, right, in a classical sense. I did look at the fractional, and so this early time, I didn't plot it and I didn't show it, but that was showing a delta right around 0.5, which would align with saying that we were in a linear flow. And then in a similar fashion, had that half slope that kind of fit more or less a quarter slope, kind of super early time and cleanup. And then I threw a boundary on just to kind of give, I like to bracket that when I'm looking at it, because usually it's transitional. And honestly, I'll show you on the next well, so I don't want to cheat kind of the concept of what I'm seeing there. But at least as it's starting to turn up, it was showing that, okay, with the delta of a 0.2-ish, maybe it's a 1.2 B factor. So maybe the transition's a little bit higher, but I think we've been hit a few times, and so I usually will default with the lower B. And then going into numerical, went ahead, and that's where I started kind of refining to get gammas that seemed to match with some of the curves in order to fit that performance. And then was making sure that I got a match there. And then this really aligned better with some of the DCA that I was doing, more so than the analytical on that front. And then in a similar fashion, really with the numerical model, I got this one to fit, and it had general agreement in what my Q would be. The OGIP, or sorry, OGIP, I almost thought I said OIP, was a little bit higher, so that gave a lower recovery factor. I would want to refine this. I do like historically doing more of a probabilistic or kind of the sensitivities, just similar ranging in order to make sure that I feel like I'm fitting a good representation of what the outcome could be, because this is, as you guys are well aware, just one interpretation. And so that was the gas well. So then jumping into the oil, very similar layout. On this one, I was actually in the reverse. I was getting lower numbers in the classical, but you pretty quickly get below your saturation, and then it becomes invalid. And so that's what I was seeing there. But then I had much tighter agreement in my numericals with a range probably in that 300,000 barrels. This was maybe a little bit light looking through. And so one thing that I was looking at in the production, because it was definitely rattier than a dry gas well, was I used the gas lift depth estimator once it flipped over to gas, because it was really looking not like it, just to the point, and I'm trying to think of a good technical term, it looked very suspect. It's speaking kind of in layman's terms, and you can see that when it's estimating where your bottom valve is, you weren't seeing that you would be hitting that. And so, to a certain degree, you're going to be in some sort of loading potentially. You're not lifting the well efficiently. And so it definitely gives you more suspect data when you're trying to analyze it. And then similarly, did the IPR analysis, got a similar PI, and then with GOR was able to fit into the PVT. So then going in and forecasting in a similar fashion, I didn't play with B factors. I would typically like to, in a normal workflow, kind of work through what my ranges could be on a DCA basis in order to see what my trends would be. But just kind of held to like 0.8 and a 1, getting in that neighborhood of 350,000 and a pretty low on the gas side. So then looking at the oil multi-phase, you definitely do see some sporadicness, and I couldn't perfectly get it to capture some of these points, but I wasn't sure if those were just outliers in the calculation for them. But was checking to try to see that in my saturations, I was somewhat aligning and agreeing to it. And so this is something I have seen with regularity, and you guys all have, where I really do like within Whitson where they'll color code, so you can see that you get that uplift and a trend off of the linear flow once you start getting into that saturated region. And since in the classical form it is for single phase, that makes sense. And so, the question that I have, kind of as you look at, I was fitting this high part just out of curiosity to see what it was getting. And it would have been a higher B factor, kind of in that 0.2 range similarly. And so maybe if I was using a 0.8, maybe early time it would be higher and then dropping. But you do start to see with that coming up that it's wanting to fit a unit slope. Some of this honestly would be, I see as liquid loading. And that's always kind of tricky, is when my well's not lifting, it is a boundary in essence. And so I always am suspect of calling it boundary dominated flow when maybe it's just a loaded well. So then I did not, and so just out of curiosity, I hadn't really played with it, but in a recombination standpoint, it definitely straightened that line back out. And so you see that, is it just a multi-phase effect? Is it filling a boundary? I got similar results, actually, when I was fitting my LFP parameter, but I kind of arbitrarily picked a point, because in this instance, it was saying it was more or less still linear, if you trust it, on that front. And then in my numerical, I did not, that is an outlier. I don't know how that didn't get deleted, so my apologies there. But I was definitely fitting a gamma closer to 4, and some of that was just trying to get that shape in order to fit my oil. Knowing that the well was had lifting issues, I wasn't sure. I didn't get good agreement on the GOR. Like, that would be something I'd want to take more time, more than an evening and in just a few minutes to try and suss out. But with it not lifting adequately, I kind of wondered what that really should look like. Because when I went into the model, I was seeing a similar uplift on that front while still getting my pressure to generally follow the trend. And so this would be something, if I had more time and other eyes, I would love to dig in and ask, because this is part on the numerical side that I would say is still a learning opportunity. So that is all I have. Thank you, guys.
So very good. I think that last model was just a little bit, you just suppress the KRG, KRO ratio a little bit, then you'll be spot on there with the perfect match. So I wouldn't worry too much about that. But just to summarize real quick on this exercise for everyone, the problem statement was to estimate the A root K from primarily the numerical model, but everybody, they went through all the time, the different steps, get a contacted pore volume, oil in place or gas in place, and an associated EUR, and using more of the tools in the toolkit. And they were going to do that by performing multi-phase RTA, and then forecast the well with the same abandonment conditions, so 10,000 days and 500 psi abandonment pressures. And again, I was primarily after the thought process. Everybody was thinking a little bit different. But if you actually go in and you look at the summary for a couple of these things, you can see that the summary for oil was pretty similar. I think that was an interpretation difference. I'm pretty sure if the KRG, KRO ratio of Avery's wells was a little bit lower, a little bit more prone to oil, there would be very, very much similarities here. And the same goes on the gas side. It was a lot of similarities. There was one thing with Avery had in his numerical model also added some unstimulated volume. So, but if you only looked at the stimulated volume, they were all in the 40 BCF range, and EURs in the 30 range. So very good work, and thank you for being so sporty. I know that's not, necessarily was something you would like to do every day, show your work on wells you don't work on or you have no relationship to, but I think it's a very healthy thing for us as an industry to do that. Now we go to the last part of the day. It's the end of the day, and it's going to be a little bit lighter, less technical items and more what I call fun. And the next presenter is a very good friend of mine and one of my own role models, Dave Anderson. He claims he has some Norwegian blood. I'm a little bit unsure about the percentage, if it's 50% or 15 or 10, but maybe you can start with educating the audience on what percentage that is, Dave. And with that, the stage is yours.
I haven't done the 23andMe, so I'm guessing it's about 25%. I don't know, something like that. I don't speak any Norwegian, so. Thanks to the Whitson crew for inviting me. It's been really cool to see a new generation of reservoir engineers discover the joys and frustrations of practicing RTA. It's brought back a little bit of my PTSD, so I'm struggling a bit with you guys, seeing you analyze these wells, but it's kind of cool. As Matthias said, I'm going to do something a little bit different here with this. This isn't a technical talk. This is actually a condensed version of a talk that I gave for Whitson webinar, I think last year, and it was about an hour long. So I've tried to pare it down and just pull out what I think are some of the good takeaways. And the idea here is, I think we've been kind of down in the weeds, which is great. We've been looking at a lot of details. Thank you for your attention. So what I'd like to do is take a step back and do more of a 30,000 foot view. How did we get to where we're at? So we can't really get better in the future if we don't understand how we got to where we are. So I'm going to give you a little bit of a history lesson, a briefer history of RTA. Where have we been and where are we going? So the underpinning sort of piece that ties all of rate transient analysis together, as you guys have seen and you're seeing with the Whitson software, there's a tremendous number of different analysis approaches and things we do that we call rate transient analysis. But the one piece that really ties it all together in my mind, well, there's two pieces really, is first of all, we always use a pressure normalized rate or a rate normalized pressure. So we're always going to start with a production rate and look at the pressures as well. By the way, this is about as technical as we're going to get here. And then we do some sort of time normalization. That appears to be, the best one to do that is material balance time. We've tried them all. Material balance time seems to work the best. So we apply these two concepts, and then really the world is our oyster. We can do all of these different things that you guys have been seeing, but that's really where it all starts. It might surprise you to know, I don't know, that I started my career in 1996 when there was no RTA. And back in 1996, I worked at a consulting company called Fetkovich Associates, and there were all these little siloed things that everybody did. So we did some decline curve analysis, we did some pressure transient analysis, mostly like conventional flow and buildup tests, material balance analysis, nodal analysis. All these things were sort of done somewhat separately with limited communication between the groups that are doing it. And the biggest difference between now and then in the context of well performance analysis is, and to me this is the biggest contribution of rate transient analysis, is it has sort of united and taken over about half of the tasks, I would say, that reservoir engineers do on a daily basis. And in doing so has made the communication between teams much better and much more fluid and much more effortless. So I really see RTA as a framework and a communication tool more than anything that sort of unites all of these different groups, all of these different disciplines. And now it's a skill set that most reservoir engineers, at least in North America, have and apply on a daily basis. So I'm going to tell you the story of RTA, identify a few milestones that I think have led us to today. You're going to see some of the characters that, at this point, the giants that we're standing on the shoulders of now. If those people hadn't come along, we wouldn't be doing what we're doing today. So we have those folks to blame, I guess, for the turmoil that we're experiencing with analyzing all this horrible daily data and trying to make heads or tails of what it means and dealing with all the uncertainty. I'll show you a couple of my examples, and no, I'm not going to predict the future. There is a sort of a nugget of wisdom we can pull from this, which is it's sort of doesn't make a lot of sense to try and predict what's going to happen in the future. I think nobody could have predicted that all this stuff we'd be doing today with these reservoir engineering tools. What I'd like to do is try and predict what I think is not going to change. And so I'll have some comments on that later. Let's look at a little bit of a timeline starting from the early days of reservoir engineering. By the way, reservoir engineering basically from a physics and math perspective was solved before 1950. So the folks, you've probably seen these guys. Well, J.J. Arps, of course, he's the godfather of decline curves. But Van Everdingen and Hurst, with the help of, or even before Morris Muscat, those folks together really did all the analytical solutions, and we still use all those today. So we've done lots of derivatives of them and made them fancier and so forth, but really fundamentally all that stuff was solved back before 1950. And so there are really three different disciplines that contributed to what we now call RTA. There's, of course, decline curve analysis, there's well testing, and reservoir simulation. Well testing primarily consisted of the analytical solutions, which were developed by Everdingen and Hurst. And reservoir simulation primarily consisted of numerical models. So, of course, analytical models are exact solutions to approximate problems. Numerical models are approximate solutions to exact problems. Both have very key usage, I think, in understanding well performance data and understanding reservoirs. And they both have their niche. And you've seen with the Whitson software and some of these case studies that folks have applied where they've used these different tools. And there's lots of details to go through there. But it wasn't always that way, right? Back when I started my career, reservoir simulation was a totally separate thing. We didn't do any of that with RTA. It was all analytical. And that was both good and bad. The good part of that is that we really understood what we were doing. We couldn't solve, there was a lot of those problems we simply couldn't solve, like multi-phase problems. But the ones that we were solving, those approximate problems, we really understood what we were doing there. So as we move forward kind of in time, really RTA became a thing before it was even called RTA. And I mentioned this when I did the full-length webinar. I think the person, if you're going to give one person credit for really a transformational view of what to do with production data, I think that would be Mike Fetkovich. I'm not sure, like at that time, what mind-altering substances they were doing to make them start thinking about using type curves for production data. But man, I'm glad they did, right? It's just sort of a totally paradigm shift, a different way of thinking about things. And so that's really where type curves first came to be used for production data analysis. And really, since then, we haven't really looked back. And that was like the 1980s. I'll talk about a couple more things on the well test side. Analysis was a huge thing on the pressure transient side that was developed by Bourdais in the 1980s. So those two tools together, the Fetkovich type curves, Bourdais, totally separate. I mean, those dudes probably never even talked to each other. They're doing completely different things, but those were both key developments in what we all do every day now with rate transient analysis. And of course, they came together a little bit later. So we're now sort of in a position where we have, widely available computer software with practical methods. We have all of these sort of luxury tools that we can use to do great analysis. I'm sort of jealous. I didn't have this at the beginning of my career. Had to develop some of them myself. So here's your Fetkovich type curve. Again, don't have a whole lot of time to go into details, but the gist of it is you develop these, dimensionless type curves. You put the analytical solution together with the empirical solution, and voila, you have this sort of great set of type curves that can basically cover, anything that you might come across in industry. And he developed presented lots of case studies, practical data. Of course, at that time, there was no flowing pressures available. This is all done with just public monthly production volumes. But he still was able to do great work with this stuff. Determine things like permeability, skin, just from this monthly production data. Let me talk about two critical innovations that happened right around 1990. One of them was the ability to reconcile the gas material balance with the existing analytical production models. We used to do production forecasting on gas wells with just a straight analytical model, which most of you know, that assumes a constant compressibility, so it doesn't do a very good job. It doesn't reconcile with the P over Z plot. And then number two is the recognition of rate pressure equivalency using material balance time. So that's when our friend, Dr. Tom Blassingame really comes into the picture. So he was obviously one of the, after Fetkovich, probably the second biggest contributor to making RTA really something that was practical and something that could be done. You guys have seen enough flowing material balances. I don't need to show another one, so I'll skip past that page. But basically, the flowing material balance was sort of the outcome of that. And Blassingame had, he had a crude version of it back then, but that at the time, that was cutting edge technology. And from about 2002 to 2006, when I was just a wee pup in the beginning of my career, most of what we were analyzing was gas. That was like the gas boom, conventional gas, and the flowing material balance was like the tool of the day, right? We used that for everything. It was great. It solved all our problems. And so we could do stuff like this. One of the main reasons for the practicality of rate transient analysis from the outset was the ability to do a production forecast on a rate restricted well, which of course you can't do with a decline curve. So the ability to have a model that was bounded by a volumetric hydrocarbon pore volume, and you could generate some sort of production forecast out of that. That was really powerful at that time. Still, I mean, that's something that with gas wells, that's something that we're doing on a regular basis. We even talked about some of that today. One of the other things that on the conventional side of things, we did identifying pressure support in water drive reservoirs. So we could do that with type curves as well. That was another big one. Moving forward in time, getting into like the mid 2000s, 2005 to 2010, that was the era of tight and shale gas. Those were the years, that's the decade of linear flow, I call it. That's where we were trying to make straight lines out of everything. A lot of the folks today were talking about some of these straight line plots. We still use them a lot, but what's happened since then is the advent of multi-phase flow and trying to analyze these much more complicated multi-phase reservoirs. The linear flow starts to go away, right? Starts to take the multi-phase behavior starts to take over a lot more. But during this period, we were like fascinated with linear flow, and I've got some examples that have like 5, 6, 7 years vertical gas well fractured with just transient linear flow for like 5 or 6 years, and so we got some great analysis out of that. Moving forward from there, if we're looking at like 2010 to current, that's of course the era of the liquids-rich horizontal multi-frac development. That's the era that we're currently in right now. And one of the reasons that became a thing, I think, is the gas market sort of fell out and has never really recovered from that. And liquids-rich became really the go-to for most operators, and that's what they're still developing these days. So one of the things that happened as a result of that is we have much more complex problems